Hello everyone and welcome to our WeAreDevelopers Database Day. My name is Sead and today we are going to talk about data platforms, databases on Kubernetes, NoSQL, Elasticsearch, GraphQL and many other topics. I want to say a big thank you to Couchbase, who are our co-hosts today and who make this event possible. And also a very big thank you to all of you joining us from all around the world. As always, feel free to use the chat beside the stream to engage with each other and to submit your questions to the speakers. After each session, we will have a short Q&A with the speaker. So take the opportunity and ask everything that you want to ask. Before we start, a small reminder about our code of conduct. Be nice to each other. Here is a small video explaining it. So, as always, we have a goodie bag to raffle out among all of you. I will ask you a question. Please submit your answer in the chat so we can try out the chat. And among all submissions, we will choose after the first session the lucky winner. So here is the question. Be prepared. The question is, what do you think is the biggest advantage of NoSQL versus classical databases? So feel free to submit your questions. As said, we will choose the winner after the first session. And with all of that said, we are going to start our first session, and we are very pleased to welcome our first speaker. He is a true expert when it comes to data platforms and databases as a service. He works as a solution engineer at Couchbase. He's focusing on application modernization, edge computing, and cloud strategies. He has led multiple teams and developed IoT solutions early in his career. So we are very pleased to welcome Gregor on stage.
So, hello everyone. I'm glad to be the first one today.
Yeah, no pressure.
No pressure.
No pressure.
Today Gregor. I'm going to talk about fully managed database services.
Perfect. So I would say that the stage is yours. We are very happy to have you here and see you after your talk.
Perfect. Thank you. All right. So today we're going to talk a bit about fully managed databases as a service, so DBaaS as it's called, what it is, what it can do, what Couchbase is, and so on. So the agenda, some insights from our customers. It's basically to get everyone up to speed, what the upcoming things are, what customers see, where the markets go into, and where data is getting developed into. Then also, what is Couchbase? If you haven't heard of it before, then details about our Couchbase cloud and how to get started. So insights from our customers. So I guess nowadays, everyone who has a data platform, they need to get somewhere stored, right? So the customers from us and all other customers have the same problems and experiences. So first of all, they need to have a better offering than their competition. So it always needs to be personalized. It needs to be responsive. Then anywhere and everywhere available. So it doesn't matter if you are on a mobile phone or on a computer or even on smart devices. It needs to be everywhere. So real-time info and inventory, that's a real big topic. So imagine in today's supply chains, if you have a product and you buy it, that someone else is not going to buy it. Also, if you need to have stock information, like how much is in stock still, this is very crucial for on-demand orderings. So also ensuring dependable transactions. So this is also a big topic. And it needs to be deployed efficiently. So delivering a great experience is the one thing, and the other thing is deploy efficiently. Of course, nowadays costs are a big factor. So hybrid clouds, edge or 5G deployments are getting more and more interesting for edge computing scenarios, but also to save costs in hybrid things, also on-premise to cloud. So this is also another thing to save costs and to make it more efficient. Why? Also to make 100% uptime and global scale possible. You can imagine if you have demands coming in for orders and your requests are spiking, then you need to scale. And only if you have a hybrid strategy or in general a cloud strategy, then you can do actually meet these demands. Flexible management options. What is getting trickier and trickier nowadays is if you have multiple installations, no matter what system, multiple public clouds, you need to manage them somehow. So each one has its own SDK and CLI, so it's getting more complex, more and more complex to actually manage them all together. And still, cost drives everything. So if you have the full possibility to go from one cloud to another in a few clicks, so this saves you a lot of money because sometimes you get better discounts on this one, or the one workload runs better and faster on this hardware versus the other hardware. So you need full flexibility to get best user experience and best costs. Last but not least, what our customers see is develop efficiently. So nowadays, resources in terms of developers are very, very limited. So getting one up to speed and having year-long trainings as it used to be before on other systems that cannot be done any longer. So what does it have to be? It must be simple, and it must accelerate my development and actually not slowing it down because it adds complexity or you need additional skills. The skills you need basically SDKs to interact efficiently and easy with the platforms. And of course, if you talk about databases, it should have a standard which is very well known and very well adapted, like SQL. All the others, you need extra time to actually learn it and also master the skills. So support best practices. Obviously, everyone wants that because you don't have to develop the wheel again if someone else already knows how to do best practice. And this is, well, all products wide. And of course, also avoiding data sprawl. So when we look at how databases changed over the time, then we need to start in the relational world. So the legacy demands, we are in a more or less transaction-based world before. As you all know, SQL was developed 40 years ago. The times were much different than now. So usually you had one search which led to one transaction. So you had small number of users. There weren't websites which had millions of users which needed to serve data. It were just limited interfaces. Some users had access to it. There were queries from time to time. How was it built? Usually these legacy systems are built on single servers, maybe for redundancy a second one. It's monolithic systems. What were they good at? They were good at obviously transaction and consistency. You can imagine if you have just one single box, then it's easier to do a transaction and to have consistency. If you have data distributed over different systems, then consistency and transactions get more difficult. And obviously also being in relational tables, storage is efficient. So what is it nowadays? So nowadays we're in an interaction world. So if you just imagine and ask yourself how you use the web for shopping, for comparing different offers, you do a lot of interactions before you actually do one transaction. So for example, in flight booking, you compare for days or even weeks the flight prices day by day, and then certainly you might decide it to. So the ratio before was usually 1-to-1, and nowadays it's 1,000 lookups to one transaction. And with IoT and big data, it's getting even more and more. So 1 million to 1 ratio is nowadays usual. We have massive data and users. The goods and the items get more and more. They have more and more descriptions and ratings and so on. All what the customer is actually basing their decisions upon. So this gets more and more. But still, it needs to be scalable and performant to match actually the user demands, to not wait minutes or even seconds on one of the results. It needs to be flexible, so no more monolithic systems, because it needs to be cloud ready. And clouds are usually multiple VMs or even microservices. So it needs to be ready for this. Also for web, mobile, and IoT experience ready. So this is the world we're living in. Still, there is a demand for relational data, but NoSQL is definitely the future. So all of this actually you can find in Couchbase, because Couchbase is the only database which combines relational data with NoSQL data. And this is basically our thing. We use SQL as a query language and still have the flexibility and everything what a new database, a modern database needs. Why is this important? Because the IDC estimated that in the next 3 years, the data which will be created will be more than over the whole past 30 years. And this was basically last year. So I cannot imagine how it's actually going. So what is Couchbase? Couchbase is, first of all, a document database, a NoSQL database, like many others that are out there. But it comes out of the box not only as a data storage, we have a lot of in-house developed, native developed services. So the first thing you need to know is that we are a memory-first database. So out of the box, we come as 2 products already. So usually you have a cache and your database. We are already these 2 products in one, because we have our managed cache built in. So what does that mean? Usually everything is first served from memory. So all the inserts, the updates and deletes, and the cache is managed by an algorithm. Usually 20 to 30% is good enough for most use cases to have in memory. Of course, if you want sub-millisecond response times, you need to have everything in memory, like big operators we have. Okay, so it is basically having the latest and most recent information in cache, and then ejects based on algorithm and time not being used out of the memory and gets new ones in. So it has always the latest information. This is why we are so much quicker than other databases, because first it serves from memory and it comes as one product. You don't need to do anything. This is basically built in. So this makes it also easy for us to do scaling, because you can imagine memory to memory scaling is much more efficient than loading anything from disk. But still, we can also do persistence first in memory, but then we have our queues which persist something. Around the core, we have then our replication layers, which makes it secure in terms of if a node goes down. But still, and this is a big difference, is that we can do transaction and joins. So we are fully ANSI SQL compliant with all the things that come together with it, transactions and joins. We can do this efficiently, others cannot. So basic service is key value. So if you store data in a document database, each document gets its unique identifier, the key. So with key value, you can then retrieve the full document out of the database using key value. This is the basic service. It's called here key value or data service, which consists of everything here. So if you want to use SQL, then you need two additional services. The query service, which parses the SQL queries and executes it. And then the index service, which again, a lot of things in memory, has the indexes built for the queries you want to do. So these you can do. Later on, this comes also very important to remember this, because all of these is individual services, all developed in-house with the same API. So next one, full text search. And here comes into play that we're not only a database, which is purely a whole platform, because full text search, you don't need an additional system for this. You can do it locally also here. So the data you stored here, you can query using full text search, and you can combine this with an SQL query. So SQL plus a full text search in the same query, this is doable with Couchbase. Additionally, you can even do analytics, and this is a shadow copy within the cluster. So the data here are getting mirrored to this service inside the cluster, which allows us to then do ad hoc queries for extremely long running queries. So heavy queries, on-demand queries you can do here. Clue here is this you can do in real time. You don't need any ETL job. Whenever something mutates here, the mutations are instantly streamed here. So no Kafka stream needed. This is all inside the cluster streamed here. And then you can use your SQL and Power BI visualization, also Tableau, and also a lot of ecosystems using ODBC, JDBC drivers can be hooked into this system in this service. Other cool service is eventing. Eventing makes it obsolete to have a middleware. You can still have it, but for example, if there's any mutation in the data, you can spawn an event. And in the event, you can modify your current data and also any other data in your database. So this makes it quite elegant. For example, child-parent relations, which are easy to do here. For example, if you have these relations, you delete the child. In eventing, you can then immediately delete all the references. You can also use it to do groupings and so on. For example, if you have a lot of IoT sensor data, you can group them with eventing. Also, REST interface queries are possible. Last but not least, we also have a mobile database called Couchbase Lite. Here, the mobile part is basically the way from syncing the core to the client. But this is another topic. Today, we are mostly focusing just on this core here, which is part of the database as a service offering, which can be deployed in all major clouds. And as a product, also in many other different products. Also in microservice, Kubernetes, we have our own operator also, which my colleague will talk later on. So with Couchbase, any cloud, any device, and many, many services out of the box. So what use cases do you have for the cloud? So I would say mostly all of them, what you have also for Couchbase on-premise makes no difference for us. The usual use cases for cloud and also for NoSQL databases is Customer 360, where you have one database which has all the customer information from different systems inside. So that makes it perfect for querying. And here you need scalability and also flexibility in your data model. Same as a user profile database. So personalization, big topic. Then catalog and inventory. Whenever you have a lot of requests, for example, in retail or for filtering, also often changing descriptions or fields where you need flexibility and scalability, perfect use case for cloud and SQL, NoSQL. Field service, so this is specific also for Couchbase. Field service are these mobile applications which need to be fed and scaled somewhere. So this data usually is stored in a backend. Backend could be Couchbase, which feeds then the mobile data. Session store, so a session database. If you browse any website, usually you create a session. This can be handled in a performant database, or also metadata management. Whenever you tag something, that you can query it quickly and modify these sessions. Identify management, also a big topic today is endpoint security, in general cybersecurity, needs to be flexible and very performant. Perfect use cases for a scalable cloud and a NoSQL database. And of course, IoT, the mother of all data collections, which has so many sensor data which need to be aggregated, stored, and queried somehow. So Couchbase Cloud, how does it work? What is it? We do it a bit different than any other cloud provider or database as a service offerings. Why? I come to that later, but this is the general architecture what we have. We don't host any of the data, right? So we host only a multi-tenant single pane of management, which is your management interface where you can configure all of this, which is multi-tenant, this we host. The rest, the actual database, is stored in your public cloud account. So this is called a VPC, a virtual private cloud, which we configured using the public API of the cloud providers using our management interface. So you basically get a multi-tenant interface where you have access to not only one cloud, but you can manage multiple public clouds at once using one interface, creating multiple databases, easily being able to communicate with each other over the management interface. So what we do for this, we create an infrastructure in the public cloud to store our data on it. So you don't have any access to it from the management interface. We don't see the data. So purely for privacy, everything you do, you get it. So management plane. So here we have our 3 different availability zones. So fully automated, also for redundancy, everything is there. So management plane, we deploy on Kubernetes. Also later on from my colleague how that exactly works, but you only need to know this works in the background with best practice. Typical adoption scenarios for cloud platform. Well, you can have your cloud native applications, but you can also do on-premise to cloud migrations to save costs, to get more flexibility. You can use the cloud for test and development instances. So they're quick to install and to run. So no need to provision any hardware. You just get it for testing and development. Also often used to your geo distribution for data gravity and sovereignty. And also often used for disaster recovery. So you can replicate your on-premise to cloud or from cloud to cloud for disaster recovery. So what you get, it's fully managed. So that means everything from deployment, operation, upgrade, scale, this is all done over the management interface. It's having comprehensive monitoring and alerting capabilities and public APIs for third-party tool integration. So you can fully automate the deployment. Inside, it is built in with our best practice. So over the 10 years what we're in the market, how to deploy Couchbase and to operate and having it available, this is all automated inside. So you don't need to take care of any high availability. You just configure it, how big it should be, and the rest is done automatically. Auto failover, auto rebalance, everything inside. Obviously, also it's secured, so with multi-factor authentication, encryption. Also, one of the biggest security factors here is that the data is secured in different locations, right? Management interface is completely different from the data interface. So it's flexible. You can have a single to multi-node deployments. Use cases also flexible, such as caching, session store, source of truth, system of records, customer 360, everything you can do with it. You can deploy it in the cloud of your choice, and it is basically configurable and scalable individually, on demand, scale in, scale out, whatever you like. High availability. It's self-healing. This is because of our most advanced operator, what also my colleague will talk about. And then also economy is great. Why? Because, as I told you, we don't have any of the data stored inside our cloud, right? You hosted data, so you get a better price for your infrastructure, and we don't put any margin on top. How to launch an application. Later on, I will show you the link, but it's very easy. You just create an account here. Oops, sorry, I clicked one too far. Then the first thing is connecting a cloud. You click on any of the public clouds in which region it should be. You connect to it. You need to have an account, obviously, in these platforms. Once the link is established, this is just 1-2 clicks. Then we can deploy infrastructure. And this is what you do in the next step. You just say, either based on different templates for different use cases, or you can completely customize the environment and then deploy it, and that's it. Then you have your fully customized database, fully performant with all features. So the single pane of management, that's what I said. It basically gives you one management interface to control all your projects and all your clusters in all different kinds of public clouds. So this gets you full flexibility to migrate with just a few clicks data from one cloud to another one. Flexibility, easy to migrate, for disaster recovery purpose, that's all included. Monitoring is also included. So in the interface, you get a very comprehensive overview of operations per second, how many connections, you can see all of this. You get also alerts, also via email if something went wrong, for example, node failure. But still, this doesn't need to bother you because the infrastructure is self-healing. So if one node is failing, another one will be spawned automatically and added to the cluster. You will just get a notification that this happened. So, also clouds can fail, and we see this also from time to time, but you don't need to worry about this. It's all displayed here, and you can monitor it. Big advantage of cloud and Couchbase is that we can actually scale our services individually, right? So you remember the circle with all the services? This is each individual service. And with Couchbase, it's possible to run each of these services individually on one node. So this in general on a cloud scenario saves you a lot of resources because you can scale only the service which actually needs more resources. For example, if your data is growing, but the queries are still the same amount, then you just can add a new node for data. And this makes it so easy and elegant to scale in the cloud, especially in the Couchbase cloud to, you just scale the services, you save costs by just scaling the service you need and want. Security architecture, always verify, zero trust. So we have encryption at rest and in flight, strong authentication, and obviously the biggest advantage is that the data is secured in your environment. If you have an application to application communication, for example, your app is also in the cloud, then it doesn't need to leave via internet. It's just local connectivity. That's it, all you need. Least privilege access, so multi-factor authentication, and in general, Couchbase has a very, very fine granular role-based access control. So you can really drill it down to the document level to say which one should actually just read and create something. Also on the cloud side, you can create users which only have access to the infrastructure creating, but not to the data and vice versa. Everything is possible to control. So complete visibility and control as it's fully automated. And we have also a fully automated intrusion and prevention detection system. Also assume the roles of our role-based access control. And we have an access control over IP whitelisting for the database access. So if you need to go over internet to the database service, then you can also just, per default, nothing is allowed and you can whitelist then your IP. Centralized management, again, decoupling of control and data plane. And this is the most critical part here, which is more secure. We don't have access to this. So even if someone hacks the centralized management, no access to the data plane. So how does a migration typically look like? Well, you have two options, online migration and offline migration. In the cloud, it is possible to also manage or add a non-cloud cluster. You need this to set up the replication from the remote cluster to the cloud. And with Couchbase, this feature is called cross-data center replication. You can set it up via the cloud control plane. So you have your self-managed cluster somewhere, can be on-premise, can be in another cloud. You add this as an unmanaged cluster and can then let it get replicated to the cloud. And that's it for migration. You set up the replication and then you can simply close the other environment down because this is a continuous replication. Once they are completely replicated, you can switch off the other one. That's online migration. Also, in general, this works for also just on-premise to on-premise streaming, again called cross-data center replication. We can truly work with two independent clusters. So we can get them replicate within just a few clicks. The other option is obviously an offline migration from a Couchbase database or any other database. You can do an CSV export and import them then in the management interface. So this is also easy. And this allows you to also add and manage, migrate any other database with it. It just needs to be CSV in the right format, and that's it. For the online migration, you need a Couchbase instance, obviously, for it. So performance, configuration, transparency, low TCO. So in general, Couchbase is usually 2 to 20 times faster node for node. Most customers, they can start with either a single node for evaluation we recommend that you go for 3 node clusters. Why 3? Because you can then avoid the usual split brain situations. So this is why we have 3 always. So all of these 3 serving data. You can go for a Developer Pro license with hourly pricing. This is the most cost-efficient way for you, because if you don't need it any longer, you can just switch it off, and the Developer Pro license is basically the cheapest one. In general, how we price is very easy. The bigger the box is, the more credits per hour it consumes. And these credits you can either buy upfront or on demand, like in a monthly, even hourly pricing. So you will be charged per month then. So these 2 options you have, and all the services I showed you, they're all included inside this, right? So it's just depending on the box, and then the bigger the box gets, the more credits you need. But that's all you need to know. And you have 2 different levels. It's Developer Pro, and for production, this is the only licenses. You as a customer choose the infrastructure as a service nodes to maximize the utilization. Obviously, this is what I said with the multi-dimensional scaling. You can scale individually the nodes. So if one service needs more resources, you just do it. You can also do a bigger box, also works. But you can also start with a small node for development and testing locals before the actual deployment. So this saves you quite a lot of costs with infrastructure. So having these 2, it saves you 75% with reserved instances from AWS. And this is the part where it comes to play what I said before. This is your AWS or whatever public cloud instance. You can choose on which instances it runs. So you can save a lot of money by doing it yourself. If you use reserved instances, for example, or if you're a big enterprise company, you can negotiate a lot better the prices than we. And we don't put any margin on top. You just purely pay the management costs. Infrastructure costs, you pay then with your public cloud provider. And then you have basically 20% with prepaid Couchbase credits. So anyway, if you choose to run this 24/7, the best thing is buying these prepaid credits. Then you get 20% off, and they're valid for a whole year. So even if you don't use all of them, you can still spin up some development and test environment, use it for, and it only expires after 1 year. And you have also flexibility in the SLAs. So as I said, Developer Pro for just developing is much cheaper than the actual production license, where you get then 9 to 5 response times for support, or 1 hour response times for critical applications 24/7. So the advantages, expertly managed with all our built-in knowledge with a whole database platform. Superior performance, and this is also proven by a lot of independent institutes which benchmark clouds and also servers in general. We are always on top of anyone else. So in VPC security, so this is obviously another advantage. We are really deployed in a virtual private cloud, which is completely secured. So we don't have access to this. So if you trust your cloud, then this is the safest way to do. Complete cluster control, and not only one cluster, it's multi-cluster management with one management interface, getting them replicated, having a hybrid cloud strategy, all with one management interface. Very easy to do with just a few clicks, nothing to do yourself here. Global deployment, so you can decide basically to have a global application which has different regions you want to serve from. With cross data center replication, you can all hook them together to have the best user experience locally for the different markets and replicate all the data among all of the different clusters. and exceptional TCO. So if you compare it to other solutions, it really comes into play that you get much better discounts and infrastructure costs. So this saves you a lot of money, actually. How to get started? Also very simple. It's basically cloud.couchbase.com and then sign up, and then you can start your free trial. You get 1 month, and if you write me or any other sales rep from Couchbase, we can also extend this for you to test with. Usually this is a self-service, but if you wish someone to explain that to you, you can also just come back to us to get help with setting it up. We can explain it to you, we can do POCs, or you can just try it out yourself and have a look at the easy configuration of the outstanding performance and the security we give there. All right, then thanks everyone for listening and hope to get in touch soon. So now is the question and answer section.
Hi, Gregor. Thanks for the nice overview. Before we start with the questions, I would raffle out the goodie bags, if that's fine for you.
Yes.
Okay, perfect. So we have chosen 3 winners, actually, instead of just 1, because of your nice answers. So the first winner is Christian Konrad. The second is Adrian Neatu. And the third one is Olli. So if you are still here, please drop us an email to hello@wearedevelopers.com with your mailing address so we can send you the goodie bags, and congratulations. So, Gregor, thanks again for the presentation. We do have some questions, which I would go ahead with. Just give me a second to open it. Lucas was asking, I saw there is already a slide in your presentation, but he's asking if there are any benchmarks of NoSQL systems versus classical ones based on performance, reliability, and so on and so on. Do you have some deeper information on that? We learned it's faster, but maybe you can add some details.
So in general, Altoros reports are a good source for this, or you just go to the website couchbase.com. There you see the comparisons. Also, what I've seen lately, a partner from us, BenchEnt. So this is also quite interesting. They have a cloud offering where you can, based on the Yahoo workloads, and so this is like an official workload, read-write shares, whatever. You can test different applications together. Also, you can look into this, so then you can try it out yourself.
Okay, thanks. Then Steffi is asking, where are the servers located? Are they inside the European Union?
So this is the clue here, right? I mean, we just host the management interface. The actual data, you decide where you want to deploy it. So you can have it in Europe, so for GDPR compliance. You can have it also in US. You decide. It's your AWS or any public cloud account where you decide where you want to deploy it.
Perfect. Someone with the nick Jeff Bezos with a P is asking what SDKs are available.
So SDKs are all the usual suspects, I would say. So C, C++, C#, then Python, Scala, Rust, Java, of course. Oh, how could I forget that? Yeah, all available for the big major ones.
And then I have a question from Christian Konrad. So Christian, also congratulations again for being the winner of the goodie bag. Who's asking, do adapters like MongoDB exist for Couchbase? We are running some services on MongoDB, but may migrate.
How you migrate? Also, there is a good blog entry from Couchbase, how to migrate from MongoDB to Couchbase. Essentially, you know, both are document databases, so it's not that difficult. You just need to get the data over. Maybe the data format needs to be changing a bit depending on the queries you want to do. And then obviously you need to change your code. But if you encapsulated everything in your own API, so this shouldn't be too difficult. But you can definitely look at the blog entry. Just look for blog Couchbase MongoDB to Couchbase migration, and then you will find it.
Okay, Christian, I hope that answers your question. If not, just please, submit a new one. And also another question from Nino, which is a bit related, like what's the difference to other systems like MongoDB? And I would also like to ask Christian, why are you considering to migrate?
So the major difference is how we actually store our data. So in all other platforms, it is basically that the provider hosts the data as well. So you need to trust the database operator to be careful with your data to secure it. We actually deploy the data in your account. So we don't even see the data. So that's the biggest difference of all. Apart from this, talking as a NoSQL platform, we actually can speak SQL, right? So we have SQL for JSON. Let that sink in. I mean, all the beauty and the familiarity you know from SQL is transferred to a JSON document, which is not relational based. So you can still use that. So that's what I also would say is the second biggest difference. And the third is the complete ecosystem. So we come out of the box as a lot of products. As you can see, I mean, we have key value, we have SQL, we have full text search, we have analytics, eventing, and even a mobile client. So all of this is a whole platform, and of course, performance. So if you look then at the Alteros report or try it out yourself, you will see that because of our architecture, and this is another session. So if you really are interested into this, you can definitely join also next month our conference, Couchbase Connect, where why we are so much faster will be explained also in a lot of details and with a lot of customers.
We will post a link to the conference in the chat for everyone who is interested. And that was already the last question, but Christian just submitted a comment. You got me with built-in KV store and in-memory cache and additional transactional safety. So that's his reason why.
I mean, if you really look into the details, other databases cannot do very efficient transactions. And this is, again, a really Couchbase architectural talk, which will be too much for this session. But if you look into the details, how we are built, that makes it easy for us to know to do a join. Because in join, you need to have different data you need to join for this, and therefore you need to know where they're actually stored. Exactly the same for transaction. If you compare our transaction performance to other databases, it's way above, because we know from architecture how to do it, and we have our built-in cache as well.
Perfect. So with that, we are almost exactly on time, Gregor. So I would like to say thank you very much for the presentation. Looking forward to have you soon again as a speaker at some other occasions. And also thanks for the audience for being such engaged. So Gregor, thanks. See you soon and bye.
And don't forget, follow-up session with my colleague with Couchbase on containers.
Very interesting.
Many thanks. Session. Bye, everyone.
Bye. Okay, we are going in a very short break, just a couple of minutes. We see each other at 1 p.m. again, Central European Summer Time. See you in a couple of minutes. Bye.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Welcome back, everyone. I am here with Denis. He has more than 14 years experience as a developer and he's speaking fluently Java, Scala, JavaScript, and Python. He is researching also on machine learning, big data, and microservices. And he will talk today about databases on Kubernetes. Hello, Denis.
Hi, Sid. How are you doing?
Good, good. How are you?
Doing fine.
Where are you joining us from?
I'm joining today from Munich.
Ah,
Germany,
cool. I
yeah.
hope the weather is fine there. Denis, what will we learn from you today?
What I'd like to talk today is a little bit about the state of the art on databases nowadays, which is making databases to become autonomous. So essentially, developers in general always expected databases to work out of the box, but historically they are the exactly opposite of that. And this is what I would say most database vendors today are trying to solve.
Okay, sounds very interesting. So, Denis, the stage is yours.
Okay, thank you very much. So, welcome everyone. This is Database on Kubernetes. Why should you care? My name is Denis Rosa. I work as a developer advocate at Couchbase. For those who never heard about Couchbase before, we are a NoSQL database, document-based, very similar to other databases like MongoDB, for instance. But the difference in our case is that Couchbase is designed for critical scenarios, right? So when you need to have performance at scale. So when you Couchbase is really highly scalable, and and this is essentially the scenarios that where we usually focus on applications that should be always on. But today, before we start, sorry, I would like to give you a small tip. Whenever you are reading an article online, if the title of the article starts with a question, the answer for this question in 90% of the cases will be no. No, you should not. Those, for instance, are all real articles from 2016 saying, should you run your database in Docker or in containers? And as you might expect, they all say, no, you should not do that at all. Back then, the main argument was, hey, containers are designed to be stateless, and databases are, I would say, the most famous example of a stateful application, right? Yeah, and that's still true, right? Like containers, in fact, are designed to be stateless. But let's fast forward to 2021, right? Now, the articles are not questions anymore, right? They are all they are affirming that, oh yeah, you should run your database on Kubernetes, on Docker, on containers, and in fact, you even see questions articles back dating from 2018 where they're already saying, oh yeah, running database in Docker at scale, right? And it's pretty interesting when you are in software development for so long that you see this shift on how the community think about a given technology. And I guess the natural question when you see this change here is, okay, what has changed? Why in essentially 2 years we completely change our opinion about running database in containers? Of course, the answer for this is a little bit complex, but I would like to at least highlight 5 things here. One is naturally performance improvements on Docker. Initially, Docker had running critical applications like databases on Docker. The performance was, I would say, suboptimal, to say at least initially. And now the performance of running something on Docker versus on bare metal is very, very close. Like we are talking about a difference between 3 and 5% in performance difference between running the database inside Docker versus on bare metal. We also have production grade images now. So pretty much all database vendors out there they have their official Docker image. And back then, most of the people running the database on containers, they were creating the images by themselves, which is obviously not ideal, because there is a lot of testing that needs to go through to make sure that the database work. Of course, like installing a database using Docker is far more easier than installing it by yourself. You don't have to deal with a lot of the configuration on the operational system and all those sort of things. In some cases, it's also very good when you can separate the storage from compute, especially when we are dealing with big data, right? It's nice to have the separation because you can upgrade the storage and separately. And last but not least, we have Kubernetes and operators, which is the main topic of this talk. Sorry. Okay. With that, I would like to I have 3 demos today, and I would like to start with my first one, which essentially shows how Kubernetes is, in fact, super extensible, right? Okay, so what I'd like to do first is Kubernetes has something called CRDs. So CRDs stand for Customer Resource Definitions. So you can define a new type of resource inside Kubernetes, right? In my example here, I'm creating a new type called to do, and the plural is to dos, right? So I have this simple YAML file here, and all I have to do to insert this on Kubernetes is to go to my web console here. First, just to show you guys, I have Kubernetes cluster here running on AWS, so kubectl get nodes. So this is an EKS cluster with 3 nodes. And if I want to install this cluster to resource definition here, all I have to do is to come to my console here and run kubectl create -f to do CRD. Okay, cool. Just added this here. And now, if I want to add one configuration for this to do, I can simply define this YAML file here where I specify the kind to do. And of course, all the parameters that I have specified on my CRD here, which is like, I have the name and the object structure here called like message and types. So I have here when in message. And if I simply run this YAML file here, so kubectl create -f to do.yaml, it will insert this configuration according to this spec here that we just added. Okay, the good thing here is now that I can run a command like kubectl get to-dos, and it will list all the to-dos that I added, right? And here we have WeAreDevs here. And if I run kubectl get to-do, describe to-do WeAreDevs, I can see the whole configuration of my to-do item here. Cool. Okay, this so far might not look like anything special happened, right? To some extent, what we did is something similar to using Kubernetes as a database, right? Because here the to-do, the table definition here would be this to-do CRD that we added, and then the to-do that we inserted right after could be something similar to our role. So we are essentially just using Kubernetes as a database. However, Kubernetes is an event-based application, and by everything that happens in Kubernetes, one event will be triggered. And when we added this, because it is an event-based application, once you add a new role, for instance, it will trigger an event internally, right? For instance, it could be like on add, on update, and same for other stuff inside Kubernetes. Like, okay, you lose a node, you lose a pod, a new pod has been started, all the sort of things. They all trigger events inside Kubernetes. And yeah, and the beautiful thing here is that you can listen to these events. So you can create applications and deploy applications that are called controllers that can listen to these events and take some action. So for instance, in order to do, one thing that we could do here is to, let's say, whenever there is a new to-do item, you can listen to this event and send an email to yourself saying, oh yeah, hey, there is a new to-do item here. So this and this characteristic here enable us to deploy applications that oversee other applications, right? So I could deploy one application that keep monitoring another, and whenever something happens there, you can take some action to try to recover from that state, that wrong state, let's say. And this is essentially the holy grail for stateful applications, because that's exactly what we need to manage stateful application. We need another application that keep monitoring your stateful application, and when something happens, you can insert domain knowledge on that application of yours that understands how, let's say, if you lose a Couchbase node in a cluster, it knows how to recover this controller or this operator knows how to recover a faulty node, right? And one of the reasons why do we have to wait for so long to have such a thing in computer science, right? Essentially because when you're managing a stateful application, most of the automation needed requires some sort of control over the infrastructure, right? So let's say if you want to scale your database, okay, you need to have some way of adding a new node and join the node to the cluster and rebalancing data, for instance. If you need to, if there is a node that is unhealthy, you need to have some way to go there and cut the network and maybe start a new node to recover from that. Right, and this is exactly one of the things what Kubernetes allows you to do. So you can deploy an operator that has some control over the infrastructure as well, that essentially allows you to oversee a state of application and recover from the states whenever something goes wrong. Cool. And why this is important for us as developers? Because yeah, we always expected databases to work out of the box, right? We always wanted to, oh yeah, I don't want to manage my database. I just want it to work. But historically, databases are exactly the opposite, right? You have to, have backups, making sure that, okay, everything's healthy there, memory consumption, CPU, and all the sort of things. So that's why we even have someone called the DBA that does that for us. And with when you deploy if you have an operator for a database and you deploy a database on Kubernetes, you can have a database as a service like experience inside your cluster. So you're not tied to a cloud provider, for instance. You can and it doesn't apply just for Couchbase. It applies for any other database. Like you can deploy MySQL with an operator inside a Kubernetes cluster, and the operator will manage your database for you. Of course, each operator is a project that each operator has its own capabilities, of course, and they are all evolving. So depending on the operator that you try, you might have different experience. But just for fun, I would like to show you guys today what an operator is actually capable of. So let's go to our second demo here. The first thing I'm going to do is I have on the same Kubernetes cluster, I have my, if I go to run kubectl get pods, you see I already have some pods running here. I will go through them in a bit. One is the operator. So I already have the operator running. You can go through the whole process on how to install the operator. It's actually super simple, just a few files that you download and install. Quite often you get the operator from the database vendor, or there is also some community developed ones that you can use. So here's one operator that is officially supported by Couchbase. And I already installed the operator here and this and the admission controller. So the admission controller is just another application that double check if the YAML file that you are adding is valid. Just make sure that you are not messing up with anything. Like, okay, but if by any chance you you add an invalid configuration that will mess up with the database, the admission controller is the application responsible for making sure that, hey, something's wrong here. You cannot do that, right? Cool. So what I'm gonna do now is to run kubectl, create -f Couchbase cluster. So this is essentially how you create a Couchbase cluster on Kubernetes. If we go back to our YAML file here, you see that, okay, yeah, what's happening here is I have specified my username and password, so administrator and password, right? This is how we specify keys in secrets in Kubernetes. Then I'm specifying here, yeah, I want one bucket called Couchbase sample. So a bucket is similar to a schema in a database. So you have like your schema there. And then I have specified I want 2 replicas. So which means that because this is a distributed database, you can lose 2 nodes and still there is no data loss because each document is replicated 2 times. Cool. And here I'm just specifying, okay, yeah, I want Couchbase 6.6. I want this cluster to be 3 nodes, and I want those services here. So Couchbase is kind of modular, so you can define which services you want. In this case, I want pretty much all services that we have. So index, query, data, eventing is something like triggers, and then analytics is, as you might guess, a service designed for analytics. Cool. So if we run here kubectl get pods, you see that we already have our 3 Couchbase nodes here. So before we visit this node, what I like to do is to also, because as I just created this database here, it is empty, right? So I would just run some commands here to start populating the database. So in fact, sorry, I will deploy an application that will keep inserting data on the database. So I will have a very simple Spring Data application here. So it's just a simple application that that insert data every few seconds. So nothing really special on here. And all I have to do is, because I already have everything ready here, all I have to do is to run kubectl create -f spring -f spring boot app.yaml. Okay, let's just double check if I have the secret here already created. I already added the secret before, because the secret is just how your application, the credentials for the database, and this is my the deployment for my application, right? So this is the Docker image that I'm loading, and then the number of replicas. Okay, just one instance is fine for us right now, inserting data. Cool. So now that we deployed our application and our cluster, I can come here and let's forward this port to my machine. So I might have here somewhere. Okay. What I'm doing right now is just forwarding port to my machine. So 8091 is the Couchbase web console. So when you install Couchbase, you get this web console by default, because this is how you manage the database or Couchbase. So we can enter administrator and password. Oops. password. Okay, and you see that, okay, we are inserting data here. So you see statistics. Yeah, here we're inserting data. And when you go to servers, you see that, oh yeah, we have here the 3 nodes. So we have one Couchbase cluster running with 3 nodes. Same, yeah, that we are seeing here on the pod. Cool. Now, let's do one thing. Let's create a new bucket. So we can add some bucket here, let's say test, and then we wait for the bucket to be ready, right? So just a few seconds. And you see that the bucket disappeared, right? The reason why this happened here is because the YAML file is the single source of truth, right? So we, in our YAML file, in our cluster specification, we have specified that, okay, this cluster has only one bucket called Couchbase sample. And now it had another bucket called test. So the operator also knows how to make the YAML file consistent with the real configuration of the database, right? So this is super cool because it guarantees that even if someone comes here and tries to change something, it won't happen because the operator won't let you to do that, because the configuration here on the database is always consistent with your YAML file. Cool. Now let's do something a little bit mad here. So we have control get pods. Okay, we have 3 nodes here, and you see the 3 nodes here as well. Let's do something. Let's kill one of the nodes here. So we run control delete pod cb example 0002. Boom. So we just lost one of the nodes of our database, right? This is when essentially the DBA goes crazy, right? Because, oh gosh, now I need to do a lot of work, right? In this case here, yes, the cluster noticed that, okay, this node here disappeared, and what I need to recover from this? Nothing, because the operator, you see, already the operator noticed that there is a new one node was unresponsive. It recovered, it killed the node. The Kubernetes brought the node back, and the operator thought, oh, there is a new node back here. So let's join this node to the cluster, right? Because the node was empty. And let's trigger data rebalancing, which is exactly what's happening here right now. So rebalancing is essentially, okay, because this new node that I brought was empty with no data, we need to move some of the data from those 2 nodes to the third node here to guarantee that the data is evenly distributed between all nodes, right? So for instance, here, because we have specified that we wanted 2 copies of the data, here, 2 replicas, 2 copies of the data. When you lost one of the nodes, you had only one copy of the data. And when you add the third one, okay, now you need to make sure copy some data from those nodes to this node here to guarantee that you have the copies that are specified. And this is exactly what happened here. I'm not going to get in detail on how some of the things happen. Essentially, we have some internally in Couchbase, the data is already sharded. So, and we shard automatically the data under the hood. So we guarantee that the data will be evenly distributed between our shards. There's no reason why you need to reshard data inside Couchbase. And we move essentially 1 shard per time. So that's how we guarantee that, okay, as soon as I move a shard, I can start redirecting traffic to this new node because he already has one of the shards there. And we just recover from a whole one failure scenario with no human interaction at all here. Cool. Okay, that's great. But you see, we did this while the application was still live, right? We recovered from the state, and from the application point of view, they would not even notice that something was happening. What if we want to do something different now? What if we want to, let's say, instead of 3 nodes, let's scale out our database, right? Let's do something like, okay, let's go to size 4. All I have to do to apply this new configuration now, it could be like 10, right? Because I have limited resources, let's just do 4. Right? So we will add one new node. So I can come back here. I already saved here. Run kubectl, replace -f Couchbase cluster. Boom. We just added this new configuration here. And now, at some point, if we run kubectl get pods, you see that, oh, there is a new node here already. It's not ready yet, so we are preparing the node, but soon it will be live, and the same thing will happen again. We will, when you go to server, okay, you see that the node is now live, and we will trigger data rebalancing again, because now we can distribute the load between those nodes to the third one. So whenever Couchbase has this kind of horizontal scaling, so if you want to double the capacity or the throughput of your node, of your cluster, all I have to do is to double the number of servers, right? It's very horizontal. And essentially what we are doing here is, as we add a new node, now some of the other nodes will move some of the data to this new node, because then the load between those nodes will be evenly distributed. Cool. What else can we do here? Well, in fact, there is a bunch of stuff that the operator could do. Like, for instance, okay, let's say I want to upgrade the Couchbase version, right? I could come here and say, okay, instead of Couchbase 6, I want now Couchbase 7.0.1, right? 1. And boom, I can come here, replace the Couchbase cluster, and we will be upgrading the database while the application is still live. Again, everything happens here while we are still rebalancing, and you see that you see documents, buckets, statistics. You see that, oh yeah, inserting is still happening here. Okay, yeah. So if we want to upgrade the database, fine. It will also be done while the application is still live. Because, for instance, the way you scale upgrade Couchbase is essentially you add a new node with a new version, and once everything is rebalanced, then you queue one of the nodes with the older version. And then you add a new node with the new version, and then once everything is rebalanced, you queue one of the nodes with the old version. So you can also upgrade the database while the database is still live. Another cool thing that we can do here is fine-tuning the database according to what your database needs. So, for instance, let's say your application reads more than writes, right? So in that case, maybe, for instance, okay, we don't need eventing and analytics, right? So those, maybe I don't need triggers in my database, and not I'm doing analytics with another tool. But if your application reads more than writes, what I could do here is to, okay, I will have say 10 nodes running index and query, and let's say 3 nodes running data, right? Cool. So I'm just making my application increasing the number of how much my read throughput, but not my write throughput. Or it could be the opposite, right? Like, okay, no, my application essentially writes more than reads, so I could do the opposite. Like, okay, now I have 2 nodes running index and query, and third nodes running data, right? So my application now can write much more than it can read. And another cool thing here is that you can adjust the hardware according to the service that you are running. So an index needs more memory, query needs more CPU, so you can adjust the hardware according to the service that we're running. Data, of course, needs a better disk, so it is also something that you can optimize here as well. Cool. let's go back here. The architecture of the operator here is, there is a lot to go through. I will share the slide later just to explain how this whole thing works under the hood. But what I would like to talk about here is like the features are far, like there are far more features that I can demo here today. We have, let's say, automated backups. So whenever you deploy your database on Kubernetes, we can do automatically backups for you. You can, for instance, you can have some outscaling. So if the database realize that, oh yeah, memory is too high, disk is too high as well, let's spin up a new node to make sure that the database is on the right state, right? It is healthy. So you can do that. Same with you can also you can hibernate your cluster. So let's say, okay, speaking of my team, we use the operator for our staging environments. But sometimes when we are not planning to push anything anytime soon, we hibernate the cluster to save resources, right? So you can do all the sort of things here via the operator. And this is a very mature solution. We were, in fact, the first database to release an official operator. And I guess if you want to, I would say today is one of the best experience that you can get for a database on Kubernetes. Of course, what I'm saying here is the same could apply, the same mindset here, the same mentality, the same ideas, they apply to other databases as well. So I'm just demoing Couchbase because, hey, guess what? I work for Couchbase. Yeah, you could have the same things that you're seeing here. Say, oh yeah, let's try this with Postgres. Let's try this with MySQL. Let's try this with whatever database you're using. They probably have at this point some sort of operator as well. Of course, you need to try the operator to see how reliable it is. But yeah, there is a lot going on, and it is one of the trends in the market in 2021. Of course, as we're talking about database, we need also to talk about storage. In this example, I was using ephemeral storage, which is not what you should be doing in production. Ephemeral is just as soon as the pod dies, you lose all the data in that pod, right? So it is definitely not what you should be doing in production. But the option, I did this just to make the configuration to look cleaner. But in a production environment, you probably will be picking something between remote persistent storage and local persistent storage. So remote persistent storage, okay, yeah, you guys know, like Rook and all this kind of things on Kubernetes. So data and a normal data storage. And local persistent storage is actually you accessing the disk that lives in the machine where your pod is running on. The only thing about local persistent storage is that it is not a general purpose storage solution, because if you're using local persistent storage, to some extent, your if the pod dies, the scheduler on Kubernetes will try to schedule the pod to run again in the same node. And this is not ideal for Kubernetes because, in theory, the infrastructure must be transparent. But in this case, specific of applications that are I/O bound, like databases, it worth the trade-offs, right? Because you get far more performance on when you're using a local persistent storage versus a remote persistent storage, because guess what? You don't have network latency, so everything is much faster. Cool. So when I should use a local persistent storage? Ideally, when the database already has replication internally. So in Couchbase case, we already have replication internally. Like we specify like, oh yeah, I run the replicas to 2. So in that case, because the database already replicates the data, you don't need to have use Rook or something to replicate the data, because it is already done internally by the database. But let's say in some relational databases, they don't have this sort of replication, especially if you are running just one node. So in that case, yes, then you need to use potentially a remote persistent storage, because then your data needs to be replicated, right? And then you might have some performance penalty because you're accessing a remote disk. So ideally, use local persistent storage whenever the database already has replication internally. Cool. But yeah, there is a lot going on our YAML files there, right? This is, I said that, okay, this is a DBaaS-like because you don't need to manage your database, but you need to understand everything that is happening in that YAML file to properly configure it, right? And depending on the size of this company, you cannot rely on developers to properly configure the databases. So there is something missing here, which is, okay, how can we make this even simpler, right? In Kubernetes, there is something called a service broker. So a service broker is like, okay, what if I could provide a service internally on Kubernetes, and all you have to do is to say, okay, I want this, let's say, package here. I want this offer, this service, this plan. is how they usually call this. So, you have like 5 plans, and I want this plan here on, let's say, for a database, you have 5 different plans. So the basic, the standard, the premium. So instead of defining the whole YAML file, you can just make a call to a service broker and say, I want the premium plan, right? And this is exactly what the service broker allows you to do, which is a facade in front of your operator, let's say, that creates an API that allows you to request the plans you want, and you can specify yourself, like, okay, what plans we have and how they would look like. Yeah, I know it is still so far a little bit not clear, but let's go to our last demo of the day and see how this works in practice. So cool. So now what I want to do now is, okay, we still have here our kubectl, all our pods, so we can get rid of them. So let's go kubectl delete -f Couchbase. Now let's say Spring Data app.yaml, and now Couchbase cluster. So we just deleted what we created before. Cool. So as you might have noticed, we have something, some other stuff here, which is the catalog, right? Which is the catalog is the service broker. I already pre-installed the service broker here, so you can go to the documentation and say, okay, this is how you install the Couchbase service broker. But what the service broker allows you to do is to do something like this here. Let me just grab the comment and say, okay, I can request to the service broker and say, hey, I want you to provision a Couchbase cluster, right, with the plan basic. And this is the password I'm going to use. So I can just make one simple call, and then it will create a Couchbase cluster here in a few seconds. So probably, of course, it takes a while, but a few seconds, but it will soon appear here. While we are doing that, let me show here what's happening. So on the service broker, you can define your plans. In this case, I have, for instance, one plan called CB standard. So, okay, on this plan CSP standard or Couchbase standard, I have here, by default, it will have a minimum of 3 nodes and a maximum. I have like outscaling, everything pre-configured, and I have 9 nodes. Like the minimum is 3, the maximum is 9. I already have like cross data center replication pre-configured, so it will already replicate to another node, and some other stuff as well. On my other plan here, which is CSP basic, which is the one that I've just show you guys. So you see here the 3 instances are already here live. But essentially on the CSP basic, which is the name that I gave, it's just 3 nodes, no cross data center replication, and minimum 3, maximum 9. Okay, and then here on the bottom, there is like all the definitions, because you are using some templates for cluster, for all this other stuff, so you can decide on that yourself as well. So essentially, you could create the plans inside your company. So you deploy the CMO files, and then the developer, when they need a database, instead of specifying the whole Couchbase configuration, all they had to do is to say, okay, I need the plan basic. And then at some point, if you need to upgrade your database, you can migrate from the basic to the pro, to the enterprise, or whatever the name you have internally, right? But the cool thing here is all I have to do to get a database is to provision a database is to call one single API. Of course, we have to discuss a little bit about, okay, when should I use DBaaS? When should I use database in Kubernetes? I would say that DBaaS is the barrier to use DBaaS is lower, of course, because you don't need to understand how Kubernetes works. Quite often, you can stay on this free tier, which is cheaper. But of course, most of the DBaaS, they will lack a little bit of flexibility and performance, because you cannot fine-tune your database, right? While database on Kubernetes, I guess it is a good choice when you have this medium and high workloads. And I guess it will give you pretty much the same flexibility as bare metal. It can automate, I would say, 80%, 9% of your work. But the downside is, you need to understand how Kubernetes works, which is still something that we are is not a common thing yet for the majority of the developers, right? Some big companies, some small companies as well, they do have the skill, but it's not. I would say it's not that common yet. So it's still, I guess, learning curve in Kubernetes is still a little bit steep, but it is getting way better compared to the past 3 years, I guess. And I think that in the near future, potentially like 2 to 3 years, those are the two choices that you make. Okay, should we run the database on DBaaS, or should we run the database on Kubernetes? You probably would never think about running the database yourself, unless you have a really corner scenarios there. But this will be essentially the two choices that we have. As you might expect, what we have done here is pretty much like how a database as a service solution works. And this is, in fact, how most of the Couchbase cloud offer that we do work. So it's kind of a slightly different version of this operator here. And as I said, everything that you learn here today is not specific to Couchbase. You can apply the same knowledge and the same ideas to other databases out there. So Red Hat has this beautiful website called Operator Hub, where it compiles all the operators that are available for stateful applications out there. And I recommend you to check it out, because they might have some operators that are could be helpful for you. If you want interested to learn more, we have we have a small book talking about our journey on building the operator and some of the things that we have learned. And of course, we also have a bunch of videos on Connect. So Connect is an event that is coming for Couchbase. So you guys, I recommend you guys to join Couchbase Connect, which is happening in 3 weeks. And that's pretty much it, what I have for today. So I hope you guys like it. Thank you very much.
Hey, Denis. Thanks for the presentation. Very interesting. We do have some questions. General question first. How much can you scale with Couchbase? And specifically, Katalin is asking, what is the maximum number of nodes you can have?
Okay. In theory, with Couchbase, you can scale to 1,024 nodes because we have 1,024 shards internally. But in practice, most clients, after like 100 nodes or so, of course, you can have one Couchbase node running. But in practice, when you have like more than 100 nodes, most clients we don't have any use cases where you need more than one database with more than 100 nodes in it. Like roughly 100 nodes is what we see in production right now for the biggest clients. But yeah, I guess that's the limit, the theory. But quite often, anything above that, most clients just decide to create a new cluster.
Okay. Then SG is asking, I think it was in your first example, didn't you lose data when the node went down?
Yeah, that's a very good question. Yeah, we don't, because here I have specified on the bucket, I have specified replicas. So replicas essentially is how many copies we have of the node, right? So because I have 3 nodes and then I have 2 replicas, it means that, okay, I have, yeah, sorry, not notice that it is, we are not sharing. So I have specified here replica. So I have copies of the data. I could specify here, let's say 3. Now each document has 3 replicas. We usually recommend like 2 or 3, which is the ideal. So having replicas, which means that if I have 3 replicas, it means that you can lose 3 nodes and still there is no data no data is lost because you have copies of the document.
Okay, then let me see the next question. So by the way, we have posted the link to the Couchbase Connect online event, so feel free to register there and join. Next question, Igor is asking if you can use JSON instead of YAML.
So that's a good question. I mean, I guess the YAML thing here is a Kubernetes thing, I guess. I'm not sure if Kubernetes allow you to use JSON for configuration. I guess the standard is YAML.
I think it does. It's not best practice, but I think it does actually.
Yeah.
Maybe someone from the audience knows exactly.
To be honest, if that is allowed, I never seen anyone doing that. So potentially, it's something that you should not be doing because the standard is to use YAML files. I mean, Couchbase store data as JSON, but Kubernetes itself requires most of the configuration files use YAML, the YAML format.
Christian Konrad, thanks for being such engaged today, is asking, where can I read about replication, especially the protocol?
Yeah, if you search for cross data center replication, so XDCR, there is essentially how we do a good documentation on how we do replication inside Couchbase. I guess replication, essentially when we talk about databases, is quite often specific to each technology. And internally in Couchbase, we have one stream of data called DCP. And the replication is essentially, as soon as you write the data to the database, we already send the data to the replication. So we have this stream of data between nodes, but this stream of the nodes can be paused and resumed. So it's very fail tolerant. And yeah, I guess if you want to learn more about how we do cross data center replication, I guess this is where you should start on Couchbase.
Okay. Then, Denis, thanks. That was the last question. Is there anything else you want to share with the audience?
No, I guess, guys, if you want to have any questions, feel free to ping me on Twitter or email. I'm very It's very easy to find me online. And yeah, other than that, thank you very much for your time, and see you guys next time.
Thank you, Denis. Bye-bye.
Thank you. Bye-bye.
Okay, we are going again in a very short break. See you in 10 minutes for our next session.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Hello and welcome back. I am here with Alex from Elastic. He is an expert and interested also in JVM, serverless basketball that I learned backstage, and also Crystal-Lang. And he will talk today about distributed search. Hi, Alex. Welcome.
Hi there. Thanks for having me.
How are you doing?
I'm good. Thank you.
Just learned that you're already also from Munich, so we have now the third session from Munich. Now we could have done it in Germany as well, this conference.
Yeah, I think the next time you can just have an in-person conference and you already got all the speakers. It's
yeah,
great.
would love to. Would love to, really. We miss that. But
Me
nevertheless,
too.
I'm sure your presentation will be interesting also in a virtual way. So maybe you want to tell us up front, what is it going to be about?
Sure. So I want to talk a little bit about like searching and finding data, but under the aspect of distributed systems and what needs to be taken into account. Of course, I'll be using a little bit of examples out of the Elasticsearch space because this is where I'm from. But I also just want to talk about distributed systems in general and like what kind of trade-offs or things you have to keep in mind, even if you just use the system, to make sure you use those in the right way.
Perfect. Then I would say the stage is yours. See you later.
All right. Thank you. So welcome again, everyone. And welcome to my session today. So we're going to take a little deeper look into distributed systems and distributed search in my case. So my name is Alex. As already told, I live in Munich. I'm based in Munich for a couple of years. I joined Elastic, I think, about 8 years ago, a little longer. I was part of the Elasticsearch team. I'm now part of the community team. So if you have any further Elastic questions, feel free to drop me an email or ping me on Twitter. So I'm happy to answer all the questions you got. So what are we going to talk about today? My goal here is just to make you a little bit more aware of understanding the complexities, the trade-offs, or the simplifications of distributed systems, right? Not everything is the same if you have a single system. And I want to just talk a little bit about why that is the case. Why sometimes you could do something easily on a single system, but suddenly it's really hard on a distributed system, also from an algorithm perspective. And I will not dive too deep into Elasticsearch itself or show queries, code samples. I really want to be more about the concepts and the ideas behind that. Before we do this, I just want to talk about in general why we're all using distributed systems nowadays, and then I want to cover the aspects of data search and analytics in a distributed environment. So let's get started with the distributed systems. Why do I need it? Sometimes you're just exceeding the limits of a single system. Maybe you need more memory, you need more CPUs. On the other hand, you can get really beefy machines nowadays on AWS, right? You can get up to 2 terabytes of memory, a lot of CPUs. So that is sometimes the reason, but not always. And you can share the load. So you can go away from a single system being loaded to several systems being loaded. You can do a certain amount of parallelization. I will talk about that in a second, what I mean with that. But you may also want to increase reliability. If you have a really beefy system and it goes down, you still have a single point of failure. So you may want to change the strategy and just go with a couple of similar, smaller dimensionized systems for more reliability. And they might also be cheaper than this one really big system. So when we talk about load sharing, then if you have a system that can sustain 1,000 queries per second, it might make sense to put an exact same system next to it so you could sustain a higher load by just running 2,000 queries per second. Of course, this is grossly oversimplified because we haven't talked about synchronization. How do we make sure that the data from the one side also always gets replicated to the other side? And also on the client side, you need to do some more logic. So you will have to do something like load balancing, which is the right part of the systems to hit. You will need to do some coordination on top of that. What happens if a system is down? So you need to add some more smart points around that. And this is one of my main points of this presentation. On distributed systems, you get nothing for free, even if it looks like that sometimes in diagrams. This is not the case. The same is for reliability. Of course, if you have this kind of replica, like I just shown, you can sustain the outage of a single node because your whole distributed system still has all of the data available. That's a huge advantage, but again, it requires synchronization. Another interesting part is the parallelization. So what you can do when you have more than one system is you could take this data, divide it by half, and put the smaller data set on 2 different nodes. And if you imagine that you could query this data in 2 seconds and you may have done some sort of a sequential search through it, then you might be able to reduce the query time because you now have less data to query. Again, this is an oversimplified situation because you still need to do some sort of reducing work, right? If you take data from A and you take data from B, you still have to merge this data together. You may need to sort this data. Imagine that this data is a time series database and the one is from an hour ago and the other one is from this hour. If you do not sort by timestamp, but by another criteria, you will have to sort this data on the client side to make sure it gets returned correctly to the asking applicant. And this is something that, again, you need to keep in mind. So you can't just say, I'm going to halve my query time with this approach because there's always some more management work to do. And a general rule around not only distributed system, but also computing is that, if you cast your boundaries wider, you will increase complexity, right? we all know that computers at some point started with a single core. It was easy to handle, right? You never had to worry about concurrent accesses, about concurrent writes somewhere into memory. It was always this one component writing and reading data that made things really simple from an implementation perspective. At some point, we got sockets with more than one core, which is also pretty common nowadays. They share some sort of memory that those two sockets can access really quick. But if you have more of those sockets in your computer, it might be much harder for the components on the right side to access data which is stored on the left side within the socket. And suddenly things become slower because you have to basically pass some wait time in order to access data. Right? Nowadays, you may know about things like NUMA, where you make sure that certain threads are pinned to a certain core or a certain socket so that the access times stay low. There are always approaches on the software side to counter those kind of issues. And the more common part is that you do not care so much about things like CPU cores, memories, but you take a computer, or sometimes just a container nowadays, and take it as a whole. And this increases or makes the complexities of those boundaries even more complex, right? Because you have a computer talking to each other. You have to make sure that each computer potentially talks to each other computer, which means the more computers or nodes you add, the more complex your communication ways will be, the more ways of communication you do have. Also the coordination, right? What happens if the first system here goes down? Like the others need to find out, the others may need to tell others, looks, I can't reach this computer, we have to remove it from the cluster, things like that. So the coordination suddenly is much, much higher than if you would just stay within your single node boundaries. And that also is coming up with the error handling. Error handling gets much more complex because on a single node, we do not assume that suddenly a CPU is not available. But in the world of distributed computer, this is kind of a normal thing that a system goes down or at least is not available. And there's a very common 8-point points of Peter Deutsch, I think, from when he was still working at Sun Microsystems. It's so-called fallacies of distributed computing, where you do certain assumptions that are just not right? The network is reliable. It's not. Like networks can fail, switches can fail, cables can fail. You may have a power outage to cause that. The latency is never zero. This is something you might not notice at all in a local area network, but the moment if distributed systems are apart from each other or the internet is in between, you will always have latency. And if that adds 100 milliseconds to all of your queries, it suddenly is a problem. The bandwidth is also not infinite. Again, something you usually don't notice unless you have to copy a petabyte of data around. Then suddenly the bandwidth is very finite. Security of the network is another common topic, right? Nowadays, when you run on shared networks like AWS or GCP, they do a lot of work to keep your data at hand, but still you're using shared resources. So you have to make sure that the communication you have is probably TLS encrypted, things like that. Then the changes of topology. If you don't own the network, you pretty much have no idea if topology changes at all or not. And the best way would always be that there's one administrator who knows your network, who takes care of that, but sometimes there's none, sometimes there's more than one doing different actions. So persons which are responsible for administering the network need to know what they do. The transport cost is zero. So what is transport cost? It could be the cost on an application to serialize and deserialize your data if you send things via RPC, JSON. But if you also go some OSI layers deeper, you may figure out that the transport cost of sending data is also not zero because you need to have network infrastructure for this. And again, that costs. And the network is homogeneous is something that you also cannot assume, right? There will be different switches, different cabling, different configurations. Maybe the MTU is changing how much of a packet you may send back and forth. Though you can never assume that the network is exactly as the same. And that, of course, gets even worse the moment you send data through the internet. So this is all things you have to keep in mind when dealing with distributed systems. And distributed systems also have one really important aspect, and that is the notion of a consensus, because they need to communicate and they need to have the same view of the world, or at least a converged view of the world, to make sure that they function properly. And this is basically known as consensus, something that you probably have already stumbled upon when dealing with any distributed system. And the base idea here is you need to achieve common state among the participants, right? In a cluster, each node should probably know where the data is that it should query. And each node should probably be aware who is part of my cluster or who's not. And there are different kinds of failures that also need to be treated, and everyone needs to be aware. There are very evil failures, like this Byzantine failures, where many consensus algorithms don't protect against. You can think of this as you sending a messenger through evil or a territory, and you don't know if that messenger arrives to send the message to the troops, or if the message gets changed on their way, if there's a man-in-the-middle attack. And how can you protect against this kind of malicious attack? And sometimes in networks, you don't have to care for this, and there's also networks where you have to take care of this. Same with trust. Is the message that I send really coming from the person that said it sends the message? What happens when a node is crashing? And this common state that was mentioned above, does it mean that every node and every participant has to see the same state? Or is it more loose that the majority of the nodes, the majority of the participants have to agree on the same state? And that brings us to consensus goals, like what do we want to do with consensus within a distributed system? And very often it's about cluster membership, like this node is part of the cluster and everyone agrees on that. It can be about data rights. So you want to make sure that the data gets written more than once. And you want to make sure that several participants acknowledge a right before you go back. And you may want to do this as part of your consensus. It may have security reasons. Think of Bitcoin. That's actually quite the opposite of the most distributed systems you're running, because they want to make sure that there's not the one party that can control everything. Whereas on the most distributed systems like Elasticsearch, it makes a lot of sense to have this one party which makes decisions. And yeah, the last part is usually finding a leader. If you have a setup where you usually have one component deciding things, you have to make sure that everyone is aware that this one node is deciding. If that doesn't happen, it usually can happen something like a so-called split brain scenario, where there are several nodes thinking that they are the leader doing decisions, and those decisions can't be merged together properly. So before we move on, and before I talk about distributed search, distributed aggregations, and distributed data management, I just want to make sure that everyone is on the same page with Elasticsearch. It's super likely you may have heard of that. And if I would need to sum up Elasticsearch as short as possible, I would just say speed, scale, and relevance as my 3 core criteria. On the outside, Elasticsearch is an HTTP-based JSON interface. So that's the lingua franca of the internet if you want to communicate with this system. Most developers know HTTP. Most developers know JSON. So at least they don't have to learn a new protocol for that. Elasticsearch itself scales to many nodes. So you can start with a single node and form a cluster, but you could also have hundreds of nodes to form a cluster. The basic idea is to always make sure to respond data as fast as possible. There's no such notion as a batch job. There are things to basically be slower with responses if you want to, because you are creating a lot of data or anything like that. But by default, Elasticsearch tries to return the data as soon as possible. The power of a full-text search engine is not the speed or the scale. The power is the relevance, right? Instead of choosing simple criteria in order to make sure that a document is part of the results or not, you can rank it. And ranking means that you can decide that a term that occurs in your query is more important than others. You could set up your query so that more recent documents, think of news articles, are considered more important, or that more popular documents are more important. Think of Stack Overflow, an answer that has been voted very high up is probably more important than an answer that has not been voted high. And apart from this, another important part for distributed systems in general is resiliency, or self-healing, or whatever you name this. The idea of resiliency is that the system itself reacts to changes so that you, as the administrator, don't have to do a lot. So in terms of Elasticsearch, if a node goes missing, Elasticsearch, the cluster itself, figures this out and makes sure that the data gets distributed to other nodes that was on this node. So we make sure that the distribution itself just works without you having to move data around manually. Another important part is the flexibility of Elasticsearch as a system. Nowadays, you can do a lot of things at query time, so you don't have to set up your index before that, like custom runtime fields or something like that. You can also do things at index time to make sure they're as fast as possible. And Elasticsearch itself is based on Apache Lucene, which is kind of the standard full-text search library. And it's the most complete library out there among many programming languages. And Lucene, as well as Elasticsearch, is written in Java. You can cover a lot of use cases with it. One of the advantages of Elasticsearch is that it's really generic. So you can just index arbitrary JSON data and search for it. But it also means that it makes a lot of sense to have concrete solutions on top. And there are solutions like maps or observability or enterprise search or security, which are already implemented by Elastic. And they just use the Elastic stack and build something on top. Or you can just build your own flavor if you want. So I started with Elasticsearch more than 10 years ago, using it as an e-commerce search engine for German B2B marketplace. So we had to deal with a lot with German language, which is not too much fun, but was an interesting experience from my perspective. German search is still hard. If you try out things like Zalando or Otto, you probably will see that. But you can also use it for things like e-procurement or for patent search. Dating websites are using it. Geo-based search is very common, like show me places which are 150 meters away from me for dinner or something like that. And then we have those solutions like observability, allowing you to ingest logs or metrics, APM data, including APM agents, enterprise search or workplace search, where you just search all the shares that you have somewhere, like Dropbox, Google Drive, Jira, GitHub, and so forth. And then we go to the security market, where you have things like a complete XDR solution. So the versatility is like an advantage and a disadvantage, because it also means you have to configure things to make sure they work the way you want it to work. So going back a little bit to distributed systems, one approach of Elasticsearch is that there's always one node which has basically the utmost management task. And that one takes a lot of decisions for other nodes and tells them what he decided on. And this node is called the master node. And one of the tasks of the master node is to ping the other nodes, right? To check if the other nodes are alive, if they're answering, if they're fast enough. And if they're not reachable anymore, he can basically say, like, this node is not part of the cluster anymore. The master node also decides where data will be placed. We will see this in a minute when I talk about charts. It can remove nodes from the cluster. It can add nodes from the cluster. It can change the data placement if new nodes are joining the cluster. But what is important to prevent a single point of failure is that the master node is not needed at all for just reading or writing data. As long as the cluster itself knows where to write the data, there's no need to involve the master node for that, because otherwise you would just create another bottleneck in there. One more important task of the master node is that it's responsible for telling the other nodes how the current cluster looks like. And this data structure in Elasticsearch is called the cluster state. And that one gets distributed to all nodes on any change. And of course, if the master node is not master anymore, a re-election needs to happen as fast as possible in order to make sure that you always have a master node. Because only if you have this type of node, an elected master, you can basically have a functioning Elasticsearch cluster. There are other distributed systems which are kind of masterless. They don't have this one leader that is deciding things. They could just use something like Gossip to, at some point, decide that they want to do something, or they don't need to decide at all. They just like write data, and if they figure out it was not meant to be for them, they can just forward this data. So there are many different approaches of how to solve the distributed systems, and this is just the Elasticsearch way. How does it look on startup? So you have a node, the node starts up. If there's no other node, the node can easily elect itself as master. Then there's another node joining the cluster. There's another node joining the cluster. If there is an existing master node, there's no need for re-election. The master node could now decide to offload data to the other nodes, things like that. But the master node itself stays the same. And a master node election is basically only needed if the master node decides to step out of the cluster out of whatever reason. Maybe the instance gets shut down. Maybe the network is not reachable anymore. And at that point in time, there will be a re-election with the remaining nodes, which also only works if the amount of the remaining nodes is having a quorum of the cluster size before that. So in this setup, this would mean that you need at least 2 nodes. Like this node 1, which is alone on the left side, would not be able to do any master node election to prevent the aforementioned split brain scenario. Let's talk about the cluster state again. Like, I just want to make sure that this kind of concept is important because, again, there are different ways in distributed systems how they see the whole cluster. There are distributed systems which just keep pinging other nodes around and get information from their neighbors. And out of that, they build their worldview and consider this the final worldview. And once enough components have talked to each other, at some point, the assumed worldview and the real worldview will be the same. That is different in Elasticsearch because of this one central node, which is managing this data structure. Pretty much all the nodes have the same view of the world. And the cluster state contains the nodes within a cluster. It contains the data, so where the data is placed, which data is placed on which nodes. It contains the mapping, so it's considered some sort of DDL for Elasticsearch, so which field has which type. And depending on the type, you use different data structures to be more efficient. And the cluster state itself gets an update when any event happens that justifies a cluster state update. And that one is sent as a diff because just out of sheer size. If the cluster state would take, I don't know, 50, 60 megabytes in memory, you don't want to send 60 megabytes to each node. You just say, look, this changed, and you send over a diff basically, so that you don't waste so much network traffic just for cluster state. Which brings us to data distribution. So I'm going to introduce a few terms, and then we see a couple of diagrams in a second. So a shard is basically a unit of work. You can consider it an inverted index, which is what you need to use to search data. And an index is just a logical grouping of shards. And you can always search across several indices. And it doesn't really matter from a search perspective if you search through a single index that has 10 shards, or if you search through 10 indices that has 1 shard. In total, you're searching 10 shards. So an index is really just a container if you want. And there's a further differentiation in primary shards. So you can say my index articles should consist of 2 shards. And when you index a document, it will be placed in either of those 2 shards. So the more of those primary shards you have, you could have some sort of write scalability. So if you have 10 systems and 10 primary shards and they are evenly distributed, you could achieve like 10 times the throughput than with a single node, because you can write more data in parallel. A replica shard is basically a copy of a primary shard that can help you with the load sharing case I presented at the beginning. And it also makes sure that there's always a copy available if one node goes down. And this is how it looks like within an Elasticsearch cluster. So you have a node that contains an index named article, and that index consists of 1 shard. This is the first primary shard. You could also have another index that consists of 2 primary shards. And if you add more nodes, only then it actually makes sense to distribute the data. So in this example, we could distribute 1 shard over to node 2, and we could also add replica shards, because copies of shards don't make sense on the same system. If that system goes down, then both copies would be gone. So copies of shards are always on different nodes. And we could go one way further. We could configure the articles index with 1 shard and 2 replicas. You can see it in the first row of indices. And we do have a second index with 2 shards and 1 replica. So each shard has 1 copy. And you can also see here that there's one system which needs to take more shards than all the other systems, because we can't just divide the total number of shards that we have here with 7 by 3. So if I now have this distribution of data, how do you search across it? How do you decide where to search? And that is the next part, the distributed search. So the basic idea here is that you have a 2-phased approach. You first query all the shards that you need to query. For each, you collect the top k hits. So if I'm interested in 10 results, you collect the first 10 results of every shard. and then create a real top 10 list out of those results. So if you query 2 shards, you would get 20 results, and you need to create a top 10 out of that. And only after that, you fetch the actual documents and deliver them back to the client. So the way this works is the client hits any of the nodes within a cluster. That's also important for Elasticsearch. You don't have to take care of the topology of an Elasticsearch cluster. You can just go to any node and query it or index it, and everything else is forwarded internally. The basic idea here is, of course, that as a user, as a client, I don't care if I'm querying an Elasticsearch cluster with 1 node or with 100 nodes. All I know is like, this is where I go, this is where I retrieve my data, or this is where I index my data. Topology is an internal implementation detail. So this node, the node number 2, now figures out which shards to query the full data set. It goes to node 1 and node 3, returns the top n results. So in this example, this would be 20, creates a real top 10 out of that, and then just fetches the documents, sort them, and returns them back to the client. And this way, you can basically specify what data, how to search in a distributed environment. The question here is, why didn't we go to the second node, which already holds all the data, and just query locally instead of incurring network overhead for node 1 and node 3? And that is a very valid question. And that brings us to the point of how to decide what to query when you have more than one shard available. And of course, you can implement this in a dump way and just say, look, I just pick shards at random. And that is usually a good strategy at the beginning. Like picking stuff at random when you don't have any idea of how to do this properly is a good idea because it prevents hot nodes or overloaded nodes. However, you can also go smarter over time and say, like, look, I just want to query the shards I know that answer faster, right? So if each node stores information of previous queries, how long they took to process, how long the search duration took, and how much space in the thread pool is to run parallel queries. And with this information, we can kind of optimize a query and say, look, this node looks a little bit more busy. Maybe it has to answer more queries because it contains more shards than the other node. So I would rather prefer sending a little more queries to the other node so that their response times even out. And this is basically what something called adaptive replica selection is doing. It's based on a paper. It's called the C3 paper. It's already a couple of years old. I think we edited it in 2015 in Elasticsearch. There's also a blog post, and I will publish the slides later on, so you can take a look. Another common strategy should be that, of course, you can hope for faster hardware to make your searches faster, but maybe a proper strategy is also optimizing your search and searching less data. And of course, we can't tell you, like, look, if you index only half of your data, your searches will be faster. So maybe you should come up with optimizations. And one of the interesting parts that has been added around 1.5 years ago in Apache Lucene, or 2 years already, is the idea of skipping non-competitive hits for top K retrieval. And we get to that in a second, what this means. And as often you don't get something for free, you usually trade something in for that. And in this example, it's the case that you do not get exact hit counts back. So the user doesn't know if you query a lot of data, if he found like 151,256 documents, you just tell them, look, I found more than 10,000 documents. There's also a dedicated blog post, but we can take a quick look of how this works. Imagine we're searching for Elasticsearch or Kibana or Logstash, and we want to get the top 10 results. At some point, the first 10 results will probably be either Elasticsearch or Kibana or Logstash, depending on their score. And if we assume in this example that Logstash itself, if a document only contains Logstash, it will not be able to reach the top 10 because Elasticsearch and Kibana have a higher score in terms of relevancy. Then we can optimize our query while it's running to something like Elasticsearch or Kibana for finding eligible documents to get into those top 10. And this is basically the idea of the competitive hits. And the result of this, of optimizing the query while it's running, was, at least for Apache Lucene, stunning. Right? You see this one steep cliff here in 2019, where you basically see a much faster query, especially on the right side. I think it's about 30 times faster. You see a second steep cliff, which was mainly because of another sort optimization. But this idea of skipping non-competitive hits led to a major speed up in the queries on a per shard base, right? So always keep in mind that there are things to optimize which may not be super obvious. Like the complete step here from initial idea to final implementation of this mechanism, which is called block max weekend, I think, always took half a decade just to make sure that the code base was in the right shape to add this feature. And there are many more optimizations within Reelsen, like using skip lists, having two-phase iterations, so you run cheaper queries first before you run the more expensive queries, compressing integers, so you need less disk space, less memory, or coming up with completely new data structures, like a BKD tree for numbers and multidimensional data. So we don't have too much time left, so I would like to do one quick overview of the aggregation here before we go to the summary. And in order to figure out what aggregations are, it's basically running on top of a query to get more insights of the document that match the query. So this could be a very common example. Yeah, if you would like to know, you're searching for all your sales from the last year, and you want to dice it for each salesperson and figure out what the total sales value by quarter is by each salesperson. Or the average response time for each of your URL endpoints per day. Or the number of products within each category. I think that's a common e-commerce use case. You're searching for new TV, and after you typed in TV something, you see on the left side the different brands of the TVs that have been found as part of the query response. And this gets suddenly a little bit more complex with distributed aggregations, because some calculations require the data to be on a single node, and that's something you don't want to do in a distributed system. Otherwise, you would have to send a lot of data back and forth, or even worse, it would not fit in your data set. So what can we do? Let's take a look at the terms aggregation. Again, we go back to the use case of counting the categories from our returned products, consider those categories. And if you now say, I would like to retrieve the top 3 of my category counts, you could just go here naively and get the first 3 results and join them together. In our example, we would end up with computers, headsets, keyboards, cables, and microphones, and a count. However, Bluetooth was on the 4th place on all of those charts and was not taken care of because it was not a top 3 result, but it would have been the first result. So you see here that when you go into this territory of counting things, you need to be really, really careful in a distributed system to not accidentally omit values. The way that this was solved over here was basically that we return more than just the top 3 in Elasticsearch, but this doesn't eliminate the problem, it only reduces it. So what we did on top of that is that we basically told the user, look, it is possible that this is not 100% exact, so this might be off by X, and we mentioned the document count error upper bound, which is when it's 0 means it is an exact count. And you could reduce this problem even further if you add more round trips to the implementation, which we have not done in Elasticsearch. That was a conscious decision for our behavior of this distributed system, but it might be a solution for other systems here. The other advantage, or the other thing that you can take a look at, is probabilistic data structures. You may know a couple of those, like Bloom filters or Cuckoo filters. The count-min sketch is a little bit known one, or the log-log algorithms, which we'll talk about in a second, or HDR and TDA just for quantiles. So those are data structures or algorithms that return a result that is not 100% exact, but trades this less exactness in for memory. And the cardinality aggregation in Elasticsearch is doing exactly that. You want to know how many distinct elements you have in your data set. And if you figure out that you have 25 distinct elements in shard 1 and 40 elements in shard 2, this information doesn't give you anything, right? Because you have no idea if those 25 from shard 1 are the same than in shard 2. So it's not helpful. You basically have a lower and an upper bound, but we can't return, like, look, we assume we have between 40 and 65 unique elements in your data set, right? That would not be really trustworthy. The solution to this is instead of returning a single integer, you return a so-called mergeable data structure. So we return something that gets collected by the coordinating node. And by merging this, we get a value that is basically much more near the actual truth without having to send all of this data back and forth. And this is exactly what hyperlog++, the used implementation, is doing. It trades a lot of memory for accuracy. So it needs only a fraction of the memory that you would actually need when you took all the data and sent it centrally to a node. And the memory usage is actually fixed. So you know before you start the calculation how much memory you need for this. And this is really important in a distributed system so that you could abort the request if it needed too much memory. And the same principle is also applying for the percentile segregation. Percentiles means that you could something like the 50th percentile would be the median. Percentiles are often used as for SLAs, so that you say 99% of my requests are faster than 25 milliseconds or something like that. And the same problem applies here, that the simple implementation where you just sort all of your values, you go to the middle of it and say this is the 50th percentile, or to the 99th part of it, and say this is my 99th percentile, requires you to have this one sorted array, and it scales with the number of documents. This is not what you want. Also, you can't merge it again across nodes. So the algorithm used here is called tdigest, which uses the so-called clustering approach. And again, it has the advantage that we can take several of those for each shard and then retrieve a proper end result. Because what we can't do again for the aggregation for the knife implementation is we take the percentiles from shard 1 and from shard 2 and just like make an average out of that. That would completely not work because it would require you to have the same numbers in both shards. So coming to the summary, I basically hope you got a little bit more of understanding of that things in distributed systems are often trade-offs. And if you don't have a distributed system, things are really, really easy. You can optimize for a lot of things, but the moment you have a distributed system, sometimes you have to accept trade-offs. The trade-offs are also sometimes about the behavior, like how is your distributed system working? How is it achieving consensus? How does it make sure that everyone has the same view of the world? It's just something you have to be sure. Like some systems need a lot of bandwidth because they're constantly pinging. Some systems don't have any central component that needs to go back and forth, and they just talk a lot to each other to convert the information. Sometimes people come up with fancy algorithms to solve a problem that didn't look solvable for a distributed system, but it comes at a price, like a 1% accuracy. And the same, of course, applies for data structures here. And yeah, the core part is just because I told this about Elasticsearch, like you take a look at another different system and it will completely accept different trade-offs. So every distributed system is really different in like how it handles certain problems. One more thing before I share a couple of more further links is like make sure that distributed systems are easy to use for the user. Like for developers, we have clients for Elasticsearch for different programming languages that basically check for the nodes in the background. So you don't need to worry which node to connect to, or if a node is failing, that is taken care of automatically. For operations, make sure you integrate with the existing tools when people are maintaining a distributed system, like be it a Kubernetes operator like ECK, a Terraform provider, or a command line tool to quickly spin up and down a cluster without much hassle. And again, I only touched a very small base over here, right? If you take a look at all of the next generation SQL databases, think of something like CockroachDB, which is called new SQL nowadays, but it's basically just a distributed SQL database. They have completely different approaches for things like distributed transactions, distributed joins. There are interesting things about collaborative editing, which is also just a distributed system. There are different things about failure detection. How do you make sure that you're really fast in detecting nodes falling about? How does recovery work? Like when one node is down, who takes over the work of the others? Like Cassandra has a feature called read repair to make sure that writes are not lost when a node goes down. But again, this approach is completely different to many others. How does leader and follower work in distributed systems? So whenever you take a look at a different distributed system, make sure you kind of figure out how those things work instead of being paged at 3 a.m. at night and then being able to debug this. yeah, I've just collected a couple of links here with framework, so you could write your own small distributed system with things like ScaleCube or SwimJava. And yeah, the important part is you understand also the consistency models. There's a really awesome tool called Jepsen, which the website above also contains a ton of reports of distributed systems and how they failed or how they broke their promise that they gave. It's really interesting to read. This is complex, so sit down and read this in a calm minute. There's also nice blog posts listing the different academic algorithms that have been implemented in Elasticsearch and Lucene over time. If you want to know more from a book perspective, take a look at this book. I think it's really, really awesome. It's already like 5 years old, I think, or 4 years old. I remember reading it quite some time ago. But it's rather timeless because it doesn't look too much at concrete implementations, but a lot about ideas and concepts. And the same also applies to database internals. I think it's 2 years old when Alex wrote it. Those are two really, really good books I can just highly recommend to wrangle with the complexities of distributed systems. All right, then I can just say thanks for lending me your ear. I hope like the next talk will be as awesome as the previous ones to just enjoy and listen. So I just wish you good last part of the conference, I would say. And if there are questions, I'm happy to answer them now.
Hi, Alex. Thank you very much. First question from my side, how can people best reach out to you? What's the best way?
Best is always just drop me an email, alex@elastic.co, or ping me on Twitter via SpinScale, depending on how public you would like your request to be.
Okay, and then a question from Matthäus was about some resources about distributed data storage. So you shared already some books. Is there anything else you would like to share? Like what's the best way to get more information? Maybe also besides books.
So outside of those books, I think there's a couple of conferences which publish all their videos on YouTube, like the Hydra conference. It's a Russian one. I think in the next days there's the P99 conference talking a lot about like achieving the highest performance. That's like for the 99th percentile. So I think YouTube is a really great resource to just watch videos to get deeper into these kinds of topics. I usually do it when doing the laundry. Highly effective to keep doing the laundry for much longer than I wanted to.
Okay, perfect. That's a good suggestion. Then Christian is asking, is Elastic now using Raft or Paxos?
No, neither Raft nor Paxos. Elasticsearch uses its own algorithm, and there's a rather long blog post explaining why Raft wasn't the right or perfect fit for what we do. One of the main reasons is that Elasticsearch needs to be really dynamic of nodes joining or leaving the cluster, and that was easier. And basically in Elasticsearch 7, the whole distributed part was completely revamped and changed with completely formally verified models. So you can take a look at those GitHub repositories as well. Everything there is open and see how this algorithm is basically implemented. But it's a custom one, highly adapted to the Elasticsearch use case.
Okay, perfect. Then Klaas is asking, how do you encrypt or hash the data?
I think those are very different things. I suppose, that's just my assumption, that it's more about how do we decide where the data should be placed when it gets indexed. And that is indeed hashing. And what we are currently doing there is a murmur hash of the ID of a document, like a unique identifier. And then we just divide modulo by the number of shards we have, the number of primary shards. So it always gets placed on one of those shards. And because we suppose you can't change the number of primary shards, the same document will always be placed on the same shard because the ID stays constant.
Okay, perfect. And there's a last question, a bit more specific also from Michael. He just got started. Can you say something about the tokenizer, when to use it, maybe with some examples?
To make this super broad, because it's not so much of a distributed thing, the tokenizer is the one component which takes a sentence that you want to index and it kind of makes words out of it, so single tokens. And the standard tokenizer is kind of using a rule set based on the Unicode consortium to say, like I split this word after white space, but for example, also when there's a dot at the end of the sentence, I make sure to remove the dot and just put the last part of the word in my inverted index. And there's something called the standard tokenizer, which is doing this, but you can fully and completely customize it for all the different rules you have. Imagine you're indexing number plates, then you need a different rule set than the one defined by Unicode for English terms. And that works with something called analysis, which basically allows you to decide the rule set of how to split the tokens to make them available for search.
Okay. And yeah, there is a thank you from Christian. And then Prasoon, maybe we can show again the books, the resources, because he's asking about the details and links.
Absolutely.
Show the...
I think you need to help me with sharing the screen again for a second. Yeah, exactly. So the first book is Designing Data-Intensive Applications by O'Reilly from Martin Kleppmann. You can also go to Data Intensive Net, I think. At the corresponding homepage for this. And the second book over there is Database Internals. It also has its dedicated homepage, which apparently I'm not. Yeah, there it is. DBaaS Dev, like the fish. And they also choose a really, really wise logo there. Both of them, and that's one of the nice parts about it, they both completely, they don't use any concrete database, storage engine, whatever. They really stay as generic as possible to explain the concepts. And that is what makes them so interesting, because you will find a lot of those things when you suddenly read about a concrete implementation, be it MySQL, Postgres, or any distributed system, of how they actually store their data and try to be as efficient as possible.
Okay, perfect. Thank you so much, Alex, for your talk. I hope to see you also at an in-person conference soon, maybe also in Munich. Would like to wish you a very nice rest of the day and see you soon again.
All right, thanks a lot, and enjoy the rest of the conference.
Thanks, bye.
Bye there.
So we are again going in a very short break before our last session of today. So see you in a couple of minutes again. We'll start at 3 p.m.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Hey, welcome back to the last session of today. I am here with William. He is a DevRel engineer at Neo4j. He's been a software developer for a long time and worked in several startups building mobile apps and financial tools, predictive APIs, and a lot of other cool stuff. He holds a master's degree on computer science, and we're very pleased to have him here. Welcome, William.
Great. Thanks a lot for having me.
Yeah, that's great. William, what will you show us today?
So I'm going to be talking about using GraphQL with graph databases and specifically Neo4j. So we'll talk a little bit about what each of those things are, but then talk about some of the cool things that we can accomplish when we combine those two technologies together.
Very cool. William, the stage is yours.
Great. Yeah, so my name's Will, and I work for Neo4j, which is a graph database, which we'll be talking about in a bit more detail. But really, the focus that I want to talk about is GraphQL and how we can really gain some developer productivity and benefits when we use GraphQL with graph databases and Neo4j specifically. So the link to these slides are there, dev.neo4j.com/GraphQL-WeAreDevs. So there's some links to resources and things like that. So if you're interested in the slides, you can just bring those up. So I'm a developer relations engineer at Neo4j, and what that means is that I work with developers to help them be successful building applications, working with data with Neo4j, and oftentimes that involves working with other technologies. So looking at integrations with different frameworks, how do I move data around, how do I build applications with Neo4j, and that really has led me to do a lot of work with GraphQL and Neo4j, which is what we're going to be talking about today. I also co-host a podcast called GraphStuff.fm, where we talk a lot about graph technologies like graph databases. So if you're interested in graphs and if you like podcasts, definitely check that out. So let's just jump right in and talk a little bit about what are graph databases and specifically what is Neo4j. So graph databases, unlike other types of databases where the data model might be a table or document, the data model in a graph database like Neo4j is a graph. So that means nodes and relationships that connect nodes. So when we're working with graph databases and data in graph databases, we're really talking about connected data, where the connections in the data are just as important as the entities themselves. We call this data model the property graph data model because we can store attributes called properties on nodes and relationships. When we're working with data in Neo4j and other graph databases as well, we use a query language called Cypher. Cypher you can think of as like SQL, but for graphs. There's an example in the upper right here of Cypher. And the thing that I think immediately jumps out the first time you see Cypher is that you're sort of drawing these like ASCII art representations of the graph. So here we're saying find address nodes. So you can see these parentheses around address are kind of drawing a node where we have an incoming registered address relationship. You can see we're kind of drawing this arrow into the registered address that's connected to an officer, that is connected to an entity where the address is in New York. This query comes from the Panama Papers project, which was a large data journalism investigation project where the data journalists from the ICIJ who were working with Panama Papers, they loaded this data into Neo4j because it was very nested and hierarchical data, where oftentimes it involved lots of nested queries to try to figure out who actually owned some interest in an offshore corporation that owned another offshore corporation, and so on. So there are lots of interesting graph analytics and data visualization things we can do with graph databases as well. And really, Neo4j is kind of at the heart of really a graph data platform where the database is kind of at the center. And we can, in this case, off onto the right, we're looking at things like graph analytics and analytics use cases where visualization and graph algorithms, graph data science, these things are used. And then to the left of this diagram, we have more transactional use cases where we're often building real-time applications. And in that case, we're more interested in things like building APIs, using some of the client drivers for Neo4j. And that is where the GraphQL integration for Neo4j fits in, which is what we'll be talking about today. So let's look at just a brief demo to see just a little bit more hands-on what using Neo4j looks like with a sample data set. So this tool is Neo4j Browser, which is like a query workbench for working with Neo4j. So I have a data set loaded already. Let's see what this looks like. So I have a data set that is users that have written reviews of businesses, and these businesses are in categories. So this is kind of the meta model of what we're working with. And let's write some Cypher queries to query this data. So first off, we're going to find a user in the database whose name is Will. And to do that, we say match. Match is like go find where this pattern exists in the graph. And then with match, we provide the sort of visual representation of the graph pattern that we're looking for. So in this case, we're looking for a single node pattern. So that's these outer parentheses are representing a node. Here we're saying find nodes with the user label. So this colon user indicates the label or the type of the node that we're looking for. And then in curly braces, we're matching on properties, the attributes of the node. And then this U becomes a variable that we can then use in the rest of the query to refer to the nodes that matched the pattern that we specified here. So here we're saying find a user node where the name property is Will, and just return that node. And we find one user node, we can see this node has a name property and a user ID property. And Neo4j Browser is a query workbench, so it has kind of some limited exploration and data visualization tools. So I can sort of double click on these and expand out. I can see here are the reviews that Will wrote. Here's the business that's connected to that review. I can see what category it's in, and I can traverse out and so on. But I can also work with this data instead of just visually interacting with it by writing more complex Cypher queries with more complex graph patterns. So let's say, let's find now all the businesses that this user Will has written a review for. So the first part of our pattern looks kind of similar, but now we're adding relationships and other nodes to the pattern. So we're still starting off with a match statement, and then our more complex graph pattern that says find this user Will, traverse out from that user node to review nodes, and then from that review node to other businesses that are connected to the review node. And so now we can see, here's this user Will, he's written 5 reviews, and these are the businesses that he has written reviews for. Now, we can also do business logic in these queries that take into account graph traversals to answer our questions. Oftentimes, that's the way that we work with the graph when we're building applications, is to say, okay, well, what's a traversal through this graph that answers some question that I have? So here we're saying, let's find recommended businesses for Will. And one way to do that would be to look at businesses that this user has reviewed, what category are those businesses in, and then to find other businesses in those same categories that this user has not reviewed. So what are businesses similar to the ones that this user has already reviewed? Those might be good recommendations, but then be sure to filter out any that this user has already been to, because those are not going to be good, relevant recommendations for this user. And we get back Hanabi ramen restaurant, another breakfast restaurant, and then a brewery that might be good recommendations for this user based on their previous activity. So that kind of traversal is fairly straightforward to express as a graph traversal using Cypher, this declarative language. You can, if you're familiar with relational databases and SQL, you can think of each one of these traversals through a relationship as kind of like a join. So as you're thinking of how you would express this in SQL, just think of how you would write all of the different joins to express this. That's sort of the equivalent, but graph databases are optimized for one, kind of expressing these sort of traversals through the query language, and then also optimized for, in the database side, those actually doing those traversals, which we'll talk about in a little bit. Okay, so that was a quick look at a sample data set using Neo4j browser. Oftentimes when we're building applications, we use the client drivers for Neo4j or different framework integrations. So for example, the Spring Data Neo4j integration that integrates with Spring Framework, or maybe the Django integration. But one way to build applications is to use the client drivers where we're sending Cypher queries. This example is in JavaScript, where we're sending a Cypher query and then we get back some results to iterate through. This is our recommendation query. So this is how we might work with the results of that recommendation query in a JavaScript application. Okay, so that's Neo4j. Let's switch gears a little bit and talk about GraphQL. So GraphQL is really an API query language, and it's all about sort of describing the data that exists in the API. And then the client at query time is able to specify sort of a traversal through that data graph of specifically which pieces of data the client is interested in getting back. So it has the strict type system that allows the client at query time to explore the data that's available. There's this feature of GraphQL called introspection, which means that we can ask any GraphQL API to tell us the schema of the API, what data is available, the type of the data, and how the data is connected. So let's look at an example of GraphQL. This is movies.neo4j-graphql.com. This is like a just a sample hosted GraphQL endpoint that anyone can query. And this is a tool called GraphQL Playgrounds, which is like a query workbench for GraphQL. So we can take advantage of this introspection feature to take a look at the data that's available in this API. And I see a couple of things. First, I see queries. These are the entry points for the API for read operations. And then I see mutations, which are entry points for write operations. And I can see the different fields that are available. So if I want to start searching for movies, I can see that movies have like a title and a plot and URL, but then they're also connected to actors, so who acted in that movie, the directors, and I can see the fields available on actor and so on. So by taking advantage of that introspection feature, we can generate documentation for GraphQL APIs, which is quite nice. So here we're searching for, just give me the first 10 movies and the title, but of course I can add other fields that I might be interested in. So I also maybe want the plot. And now let's add all of the actors in each of these movies. And you can see as I add fields, the result matches the shape of my query. This piece of the query is called the selection set, which specifies two things. One, the traversal through the data graph. So I want to go from movies to actors, And I can even look at other movies that those actors acted in. That's the traversal through the data graph. But then the selection set also specifies the fields to return. So movies, the movie type has a lot of different fields, but I'm only returning title, plot, and the actors' connections. And this is useful because in my application, I may only need to render certain pieces of data in the view of my application. So I don't want to send back all of the movie data over the wire. That can be more data than my client application needs to actually work with to render the view of the application, and that can slow things down. Similarly, I can, from the client, specify all of the data in one query that I need to render the view of my application. So this is quite nice because I don't need to then send multiple queries to the backends, which again can be slow. So those were two aspects that were sort of the original goals in GraphQL's design. So GraphQL was designed and built inside Facebook and then open sourced in, I think, 2016, something like that. And those were the two problems that Facebook was trying to solve, which is sending less data over the wire, and then also making sure that we're only sending one request to the backend. Okay, so that's a quick look at an example GraphQL endpoint. Now that we've talked both about graph databases in Neo4j and GraphQL, let's compare these two and talk about when we would use one, when we would use the other, and why we would use both of them together. So we said that Neo4j is a database that uses the property graph data model. We have this Cypher query language, which is declarative and very expressive for working with graph data. We can also do things like graph analytics and visualization, these sorts of things. And the database itself is optimized for these graph traversals, similar to like what a join would be in a relational database. Now, GraphQL is all about building APIs. So GraphQL is very much not a database query language, but it's something that we would build an API layer to expose some data that's in our database to the client application. But we also are working with the graph model with GraphQL. When we combine these two technologies, we have a lot of benefits. One is we have this now type-safe API layer. So one thing about Neo4j is that we don't have the concept of schema in the database. It's meant to be a very flexible data model. We do have things like constraints that we can build up, but there really isn't the same concept of schema that we have in, say, like the relational database world. So when we use GraphQL on top of Neo4j, we have this type-safe API layer that can almost act as a schema for the database. And of course, we have this unified graph data model. Now we're talking about graphs on the client in the API layer with GraphQL that map directly to the graph data model that we're using on the back end. And to make using these two technologies together easier, there's an open source library called the Neo4j GraphQL library, which is all about building GraphQL APIs with Neo4j and taking care of a lot of the often boilerplate work that we would do to build GraphQL APIs. So let's compare Cypher and GraphQL, because I think this is an interesting question that oftentimes folks ask, which is, well, you said that GraphQL is not a database query language, but Cypher is, but they're both working with graphs. What's the difference, and sort of why do they both exist, I guess? So let's look at an example using what I call the news graph. So this is data that comes from the New York Times API that we've then built a GraphQL API on top of. And you can find the code. The code is linked here on GitHub, as well as where you can fetch the data from the New York Times API. But basically, we have articles. Articles have a topic. They may mention organizations or people, or they may mention specific geo-regions. They have data such as photos and the author who wrote this article. Then we have things like comments and replies to comments in the thread as well. So we've seen some examples of working with Cypher. We have these declarative ASCII art patterns to work with data. One thing that we didn't really talk too much about is that Cypher has a lot of functions for working with data similar to what we would find in SQL or other database query languages, things like aggregations, math functions, database operations like creating indexes, and even things specific to handling data import like loading a CSV file. And then we also have lots of graph-specific operations like this concept of variable length paths, finding the shortest path, these kinds of very graph-specific functions. Whereas if we look at GraphQL, we have this concept of a type system, and we're still working with graph data, but GraphQL really can be built on top of any backend data layer. So it's not specific to a graph database. We can build GraphQL on top of relational databases, on top of other NoSQL databases, even wrap other APIs, and so on. And really the core of the GraphQL query language is allowing us to express these nested traversals through a data graph, which is that selection set. So let's take some use cases for our New York Times news graph and see how we would write Cypher queries and GraphQL queries to fetch that data. So show me all the articles. That's simple enough to express in Cypher. This is similar to our user graph pattern that we were writing earlier, except now we're not filtering for a specific property value. Just show me all of the articles. And in GraphQL, we would do something similar. So assuming we had a GraphQL API, we might start at the articles entry point and then bring back whatever specific fields we're interested in. Show me the 10 most recent articles. Well, Cypher has built in the ability for sorting and ordering by a specific field and limiting to only return a subset of the results. GraphQL doesn't have this sort of sorting built in, but of course we can express that through field arguments in GraphQL, where we're saying the sort should be on the published field in descending order and only return the first 10 results. Now, if I want to say, show me the first 10 articles and their topics, well, we add a bit more complex graph traversal to our graph pattern in Cypher to do that. This one looks a little bit different than what we saw before. Here we're using an optional match because it's possible that some of our articles don't have topics, but we still want to return those. But conceptually, it's very similar to what we saw before, where we're just adding this additional traversal. So once we found the article, traverse out to the topic nodes. To do this in GraphQL, well, we would just add topics object to our selection set here. Now a bit more complex, show me the 10 most recent articles, their topics, and now from those topics, traverse out to other articles in those topics. So this is if I'm looking for articles that are similar to the one I'm currently reading, something like that. And to do this, again, we just add that extra piece of the graph traversal to this graph pattern in Cypher, to our sort of ASCII art representation. And in GraphQL, yep, we would just add an additional nesting in our selection set to now go out to other articles from those topics. But what about more complex things like show me the shortest path from one node to another? Well, in Cypher, we have this shortest path function and this variable length operator. So this says find the shortest path from Vladimir Putin to the topic extortion and blackmail up to 9 hops deep, and we get back the subgraph that represents the shortest path. GraphQL, though, we don't have anything built in GraphQL that would allow us to express that. Similarly, something that's business logic focused, such as show me recommended articles, we can write a query in Cypher that says, well, recommended articles probably have overlapping geographies or topics or authors, so let's find similar articles that way. GraphQL, we don't really have a built-in way of accomplishing that. Of course, as we implement the backend GraphQL server, we can express that in our GraphQL resolvers, which we'll talk about in a minute here, but we don't really have any built-in way to express that in GraphQL itself. So hopefully that gives some idea of why Cypher, which has a lot more sort of database-specific functionality, exists alongside GraphQL, whereas we wouldn't necessarily want to expose our database to a client application. So let's say, for example, we have this news graph and we want to build a news reader. So maybe a mobile application that's a React Native, or a web application that's a React application, where we want to allow a reader to read these articles, find similar articles, this sort of thing. And we have this data stored in Neo4j, running in the cloud and on like Neo4j Aura. Now, we don't want to just expose this database for anyone to have access to in the client. We may have some things specifically that we want to build in this API layer, such as authorization rules. Only certain users can access certain pieces of data. Maybe we want to implement some caching, some things like this. So this is where GraphQL comes in. So rather than querying the database with Cypher directly from the client, we have a GraphQL API, and our client application is querying with GraphQL. The API layer is translating that GraphQL into Cypher, sending that to the database. So we've talked about using GraphQL. Let's talk a little bit about how we would actually build these GraphQL APIs. And there's sort of 3 parts to this, I guess. One is building GraphQL type definitions. So this is the schema for our GraphQL API that describes the data that's available, the entry point for the API, and so on. Then we need to implement what are called resolver functions. And this is really the data fetching logic for our GraphQL API that actually has the logic for going out to the database and fetching data or updating data based on the GraphQL operation. And then the third part is the networking layer. How do we serve this GraphQL schema? How do we take network requests, execute those against the schema, and then send results? So there are a few ways to create GraphQL type definitions. One of the most common is to use the GraphQL schema definition language, or SDL, which is this kind of language agnostic way of expressing the GraphQL types, the fields, and how those fields are connected. We can also do this programmatically, but with the programmatic, or often it's called the code first approach to building GraphQL types, they're specific to whichever GraphQL implementation you're using. So if you're using the Node.js GraphQL implementation, the code is going to look a certain way. There are GraphQL implementations in pretty much any backend language as well. So it'll look a little bit different in Python or Java, this sort of thing. So SDL is nice because it's language agnostic, and regardless of what language the backend GraphQL server is implemented in, it's something that can be understood. Then we have these resolver functions, and the resolver functions may do something like check for authorization or permissions. They might query a database. They might validate, format the response from that database. So any of that sort of logic is defined in these resolver functions. here's a couple of different examples of resolver functions from just a couple of different projects that I've worked on. You can either do something like send a database query directly using a database driver, or you may use like an ORM API, which is this one on the right, where we're working with conference sessions and what rooms they're in, the theme of the session, and so on. But one thing that I want to point out with this example on the right, where we're using this ORM type syntax, is that these resolver functions are called in a nested manner. So we start with the root resolver, which in this case, we're searching for sessions. That's a field on the query type in this case. So we'll make a trip to the database to find sessions that match some search string. But then if we also ask for what room that session is, we have to go back to the database to say, okay, for all of the sessions that we found, tell me what room those are in, and then do the same for the theme and then for the recommended. So we end up making a lot of round trips to the database to resolve just one GraphQL operation, which that can have performance problems. And this is called the N+1 query problem. So if we're looking at building a GraphQL API with Neo4j, sort of call it the naive approach would be just to use the Neo4j client driver in a resolver function, and you have a Cypher query that you execute there. And this works okay for some things. We use this approach, for example, on the Neo4j community site, where we have a leaderboard that's showing the most recent activity and neat projects from the community. This works if we have sort of a very simple static query that we want, that we don't really have any need to handle a different dynamic selection set from the user. Other common approaches, and this is similar not just to Neo4j, but with other databases, you might use some framework-specific integration. So Neo4j has a Spring Data integration that we can use with GraphQL frameworks to build a GraphQL API. But these are some of the common problems that come up when we go through these approaches, where we're sort of implementing these resolver functions. We end up maintaining a schema for the API, one for the database. We have this sort of mapping and translation layer if we're not using a graph on the back end. And we end up writing a lot of boilerplate code. So how do I set up a connection to the database? How do I use maybe the ORM API to search for matching fields, this sort of thing. And then we talked about this N+1 query problem, where we end up sending multiple queries to the database for a nested GraphQL operation. So to address some of those challenges, the Neo4j GraphQL library was created. And this is a Node.js library that can take GraphQL type definitions and generate a fully functional CRUD GraphQL API. So with all the entry points, all of the filtering, pagination operations. And then at query time, it translates any arbitrary GraphQL operation to a single database query, to a single Cypher query. So that addresses the N+1 query problem. So we're only making one round trip to the database for any arbitrary GraphQL request. And then we're also taking care of this boilerplate problem where I have to implement all of these resolver functions for every type and field in my GraphQL API. We don't need to do that with the Neo4j GraphQL library, because all of those are generated for us. It has a really neat feature also that allows us to use Cypher to define custom logic in the GraphQL schema, which is really nice, and other built-in functionality for creating authorization rules in the schema as well. So those were kind of the high-level goals: reduce boilerplate, improve developer productivity so that I can get a GraphQL API up and running without writing a lot of code, but then also being extensible to add custom logic and focused on performance. The performance characteristic here is interesting because graph databases, we talked about being optimized for these traversals through the data graph. And oftentimes in GraphQL, we're writing these very nested queries where our selection set is traversing through this data graph. So graph databases that are optimized for these data traversals end up being a really good fit for GraphQL APIs, because when that query comes into the database execution engine can then optimize that query at the database level. So with the Neo4j GraphQL library, we want to support this idea of GraphQL first development, where the GraphQL schema is then driving the database model. So we write our GraphQL type definitions, and that drives the database model in Neo4j. So we don't need to maintain two separate schemas. And we talked about this idea of auto-generating the CRUD API, so adding entry points based on our type definitions, and then other functionality like pagination filtering as well. I'm going to skip ahead a little bit and take a look at a demo so we can see what this looks like really quickly. Here we go. So this is a code sandbox, and the link to this is in the slides as well. The code's also on GitHub. And basically what we have here is a GraphQL schema. So these are our GraphQL type definitions. We have some additional, they're called schema directives. So directives are like annotations on a field in GraphQL. There we go. That add a little bit more information. So the property graph model has, every relationship has a direction and type, which we don't necessarily have in GraphQL. So that relationship directive is capturing that. And then you'll also see here we have this recommended field, which has a cipher schema directive attached to it, where we have this cipher query. So that's how we add custom logic to our GraphQL API with annotating them with cipher queries. So this says, for this business, let's find users who have reviewed this business. What other reviews are they, or what other businesses are they reviewing? Those might be good recommendations. So something similar to that collaborative filtering query that we saw earlier. So to build a GraphQL API with Neo4j, we write those type definitions, and then basically we're just pulling in our dependencies here and reading our GraphQL schema, passing that schema to the Neo4j GraphQL library, create a Neo4j driver instance to connect to our database, and then we just pass that to Apollo server, which is a Node.js GraphQL implementation. But we don't need to write any resolvers, so we don't need to write any logic that specifies how to actually fetch that data from the database. That's all handled by the Neo4j GraphQL library. So here we're searching for businesses and their name, and we can see in the logs here the generated cipher query. So as we add more fields to our query, let's bring in the address and maybe any reviews that we've had, the user who reviewed it, and so on. We can see this more complex generated database query here. And if we add our recommended query, so that was a custom cipher query that we defined as an annotation to find recommended businesses. That still generates a single database query, just essentially taking this cipher query that we've annotated our GraphQL schema with and running that as like a subquery in our single generated database query. So that's a little look at the Neo4j GraphQL library. There's a bit more examples in the slides here that I'll skip over in the interest of time. But if you're interested in thinking about how we work with GraphQL and Neo4j in the context of a full stack application, there's this podcast application that we built on the Neo4j live stream that kind of talks about that. And then a bit more in the slides about the authorization functionality. So if that's interesting, check out the slides, which are available. I want to leave with just talking about a couple of resources if you're interested in learning more about working with GraphQL and Neo4j. The first one is sort of the landing page for the Neo4j GraphQL library, which has some examples and links to the docs and this sort of thing, which is dev.neo4j.com/GraphQL. And there's also a self-paced online course for building GraphQL APIs with the Neo4j GraphQL library that's available on the Graph Academy, which is like the online learning center for Neo4j. I'm also working on a book that's published by Manning called Full Stack GraphQL, which touches on a lot of these concepts, but also brings in a lot of the front end and full stack considerations for how do I deploy this in the cloud, how do I add authorization, this kind of thing. So that's available in pre-release now, although I think the first draft, at least, of all of the chapters are out now. And then finally, we do have a Neo4j live stream. So if you are interested in live coding on Twitch or YouTube, that sort of thing, check out the Neo4j live stream. I'm working on a series now building interactive graph visualizations with Neo4j and GraphQL as well. So do try to check that out as well if that is your sort of thing. Cool. And with that, I think if we have time to take any questions, maybe. But otherwise, thanks for watching.
Hey, William, thank you very much for the presentation. I hope you enjoyed it. I'm sure the audience did. I would say let's jump right into the questions.
Great.
Alex is asking, do you think it makes sense to build a GraphDB layer on top of an existing RDBMS for analytical purposes?
Yeah, so I think oftentimes you'll find if you're using a relational database, you often run into some performance or data modeling issue that often lends itself to be better solved by a graph database. So for example, I worked a while ago for a company that was calculating commissions for different offices. So kind of like a multi-level marketing kind of thing where the commissions for one office depended on the sales of the parent office and this sort of thing. And it took several minutes to run this report in the relational database they were using, which I think was MySQL or something like that. And so we looked at using Neo4j to do this. And because graph databases are optimized for these sort of nested traversals, it took like less than a second to run this. So I think in the case where you already have a relational database that is kind of your source of truth, but you have some performance problems or some data modeling issues, it can make sense to then sort of introduce a graph database like Neo4j to take care of those specific queries and issues that the relational database can't really handle. So that's a common approach. But I think also you can also think of using Neo4j as your primary database. For a lot of operations, Neo4j is just as good as a relational database. And then you have the benefits of where it can excel, which is typically in things like these operations where you're doing a lot of joins or complex data models. So I would say you certainly can introduce a graph database alongside a relational database, but you might not need to have that relational database in the first place, especially when we're looking at tooling and framework integrations like this GraphQL API. You could envision just sort of building that GraphQL layer on top of Neo4j and that being your primary database for your application.
Okay. You showed us that you don't need to write your resolvers because they are auto-generated. And Ellie is asking if you still have the possibility to add custom-made resolvers to extend the auto-generated ones.
Yeah, absolutely. So if you have more custom logic, you want to call out to a different system or something that you can't express as one of those cipher directive fields, yeah, you can just implement a resolver and override the generated resolver, and that works just fine. The only thing to think about is when you do that, then that resolver is called in the nested fashion as well after the generated resolver. So you may lose that one round trip to the backend because that resolver will be called after the first resolver that goes to the database. So just something to think about, but yeah, that's absolutely possible.
Okay, perfect. And yeah, Michael is asking, is migration easy from GraphQL JS?
So I think that question might be related to if we've built a GraphQL API using different tooling, and we then sort of have this generated schema for us with the Neo4j GraphQL library. I think that's one thing to think about, is that the Neo4j GraphQL library has sort of a specific type of schema that it will generate for us with certain field arguments and that sort of thing that might not match something you've built previously, which then might require some updates mostly in the client, I think. The GraphQL type definitions that you use are probably going to be pretty similar, but that might be where some of the migration work is on the client, since the generated API might be a bit different.
Okay. And then the last one from Rick, he's asking, how do you secure the API?
So there are a few ways to go about that. The Neo4j GraphQL library has built-in functionality for working with JSON Web Token. So assuming you're passing a JSON Web Token as like an authorization header, you can then define authorization rules in the GraphQL schema that say things like you need to be a authenticated user to access this field or this type, or you need to have a certain role based on the token, or even more property value based authorization rules, such as you need to be the author of this blog post in order to be able to access it. And there's a section that I skipped over in the slides that talks about that in a bit more detail. There's also a section in that online course that I mentioned as well that goes into a lot more detail. So that's kind of the built-in way to approach that. There are, of course, other ways you can take with like middleware and things like that. But I'd say if you're using the Neo4j GraphQL library, just using that built-in authorization schema directive is probably the easiest approach.
Okay, perfect. Thanks. Well, that was the last question of today. So I want to say a big thank you for getting up so early to join our conference here. I wish you a very nice rest of the day and see you hopefully soon again.
Great. Thanks a lot.
Thanks. Bye.
Cheers.
So, as I said, that was our last session. We had amazing 4 sessions behind us, but next week we are coming back with our next virtual conference. Actually, it's a hybrid conference, so we are going to talk about coding the future of mobility. We will talk about cyber security in autonomous driving cars. We will talk about software architecture, microservices. We will talk about getting started with machine learning. So join us on October 6th at 9 a.m. with a workshop about E2E architectures. And then in the afternoon, we will have a couple of nice talks and presentations. So make sure to be there when it starts. And yeah, so far I can only thank you again for joining us today. Wish you a rest of the day, a nice rest of the day and a nice rest of the week, and see you next week again. Bye-bye from WeAreDevelopers.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Hey, I see there is still some people watching, but it's over. See you next week again. Bye bye.